Somewhere in the dark between galaxies, an object that only swallows could meet an object that can only spit the universe back out. One is a black hole, the ultimate sink. The other, a white hole, the forbidden fountain. If they collide, does space-time tear, flare with a signal we could see, or snap open into a newborn universe? In the deep architecture of reality, there are rules so strict that even light must obey. But when two horizons carry opposite boundary conditions, the rulebook itself begins to tremble. What follows is not a monster story told in metaphors, but an audit of the universe under extreme stress, where geometry becomes destiny. In this documentary, we treat the collision as physics would. Not a simple impact, but a rearrangement of spacetime's causal map. Event horizons are not surfaces you could touch, and yet they decide which futures are permitted and which are erased. A black hole's horizon is a one-way boundary written into the direction of time, and its signature is already etched into our instruments. We have heard their mergers as gravitational wave chirps, watched their surroundings blaze in X-rays, and traced their shadows against hot plasma. A white hole, by contrast, survives mostly on paper, an exact solution that looks clean in equations, then frays the moment the real universe breathes on it. If such an object could persist, it would demand an almost impossible arrangement of initial conditions, and it would challenge the arrow of entropy at every step. That tension is the real stake here, because it asks whether the cosmos can host a sustained reversal, or only fleeting imitations. We will build the groundwork with what is known, then carefully introduce what is only implied by relativity's symmetry. Along the way, we will use Penrose diagrams to make causality visible, light cones tilting, infinities compactified, and horizons revealed as global decisions. We will ask what it even means for two horizons to meet when an event horizon is defined by the entire future of space-time. We will test the encounter against 5 filters: consistency in classical relativity, stability under perturbations, survival in an astrophysical environment, the demands of quantum gravity, and the signals an observatory could actually measure. The universe is not empty, and even a thin bath of photons and neutrinos can become lethal near a horizon through blue shift and focusing. In that hostile setting, the central question becomes a race of timescales: orbital in spiral against instability, emission against back reaction, theory against noise. We will follow the geometry into the moment of closest approach, where 3 broad outcomes compete without revealing their final winner. One path looks ordinary from far away, another could burn briefly with exotic transients, and the most speculative path retreats behind a boundary that may never report back. Yet even silence can be informative, because gravitational waves carry bookkeeping in phase, amplitude, and ring down that no metaphor can hide. If an impossible boundary condition ever left a fingerprint, it would be written there, in subtle shifts, missing absorption, or echoes that arrive late and faint. And if it did not, that absence would still teach us something sharp about causality and the generalized second law. This is an exploratory journey through the most unforgiving regimes of physics, where every claim must survive geometry, thermodynamics, and observation. We are not chasing certainty, we are chasing constraints and the shape of what reality refuses to allow. In the end, the question is less about fantasy than about foundations, what space-time can do, what it cannot, and what it might do only once. The camera will linger on darkness, but the story is about rules, how they bend, how they harden, and how they may finally be rewritten. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by mapping horizons as causal boundaries, then climb from observed black hole mergers into the theoretical shadowland where white holes reside. From there, we set the trap for an encounter, track what detectors could hear, and end at the edge of quantum gravity, where the verdict may be stranger than either side alone. Somewhere between galaxies, 2 extremes drift toward the same point in space. Slowly at first, then with the quiet certainty of gravity. One is a black hole. It admits matter, light, and time, then never returns them. The other is a white hole. It would expel matter, light, and time, then never accept them back. If they meet, does the universe blink, break, or rebalance itself? This is a thought experiment with real stakes. because the objects are defined by boundaries rather than surfaces. Horizons are not just edges you could touch. They are one-way limits written into space-time itself, limits that decide which futures are allowed. A black hole sets a limit on escape, and it does so for every kind of signal. A white hole would set a limit on entry, forbidding even a single photon from crossing inward. Put both limits in the same region, and the causal map of space-time may tear or snap into a new pattern. To picture that map, imagine a grid drawn across the darkness, with arrows showing which way tomorrow points. Near a horizon, those arrows tilt. At a black hole, they tilt so far inward that every future path falls deeper. At a white hole, they tilt outward, as if the future itself is being pushed away. The question is not only where the objects are. The question is what happens to the arrows when two incompatible one-way rules approach each other. We start with what is solid, because one side of this encounter is no longer hypothetical. Black holes are predicted by general relativity and seen through their effects, from stellar mass remnants to the supermassive engines of galaxies. In the simplest case, the Schwarzschild solution describes a non-spinning hole with a spherical event horizon. In the realistic case, the Kerr solution describes a spinning hole with frame dragging and an ergosphere, where space-time is pulled around like water in a whirlpool. These are not exotic guesses. They are the standard geometries that match the sky, and they have survived every precision test we can throw at them. Historically, even black holes began as a strange implication of equations rather than an observed object. In 1916, Carl Schwarzschild found his solution while general relativity was still new, and the radius where the math looked singular seemed like a defect. Decades later, better coordinates revealed that the event horizon is not a physical tear in space-time. It is a coordinate-independent boundary, real in its consequences even when it looks smooth locally. That shift in understanding matters here, because white holes also live in the difference between what looks singular and what is physically unavoidable. A black hole's event horizon is not a material wall, it is a boundary in space-time where all future directed paths point inward, including the paths of light. Cross it, and every possible trajectory leads deeper, toward a central singularity in the classical picture. Outside it, gravity still rules, but escape remains possible, at least in principle. Inside it, out stops being a direction you can choose, because the geometry has redefined what directions mean. That redefinition is subtle, and it is easy to miss if we imagine space as a stage. In relativity, the stage is part of the play. A horizon is where the light cones tip so far that even a rocket firing at full thrust cannot aim its future outward. For a distant observer, clocks near the horizon appear to slow, and signals grow redder and fainter. For an infalling traveller, nothing special marks the crossing, until tidal forces, depending on the black hole's mass, begin to dominate. Around many black holes, matter forms accretion disks that heat and glow, turning gravity into light with brutal efficiency. Gas spirals in, converting gravitational energy into radiation before vanishing, and frictional turbulence drives temperatures to millions of degrees. In X-rays, the inner disk can shine like a hot ring around a void. Jets can launch along spin axes, powered by magnetic fields and rotation, and they can punch across intergalactic space like luminous spears. Tidal forces stretch objects into long streams, then shred them into plasma, creating flares that briefly outshine entire star systems. Black holes announce themselves by what they disturb, not by what they emit. We have also heard black holes collide, and the sound is written in gravity itself. Gravitational wave detectors have recorded the ringing space-time of mergers, where the signal rises in pitch and amplitude like a cosmic chirp. Two horizons approach, distort, and finally become one, while the surrounding geometry radiates away the last asymmetries. The final object settles down in a process called ring-down, like a struck bell losing its overtones. In these events, the collision is not a crash of surfaces. It is a rearrangement of geometry, and the geometry is the only thing that truly touches. So what does collision mean in our question? It could mean a direct merger where horizons overlap and form a single trapped region, leaving one combined boundary to rule the future. It could mean a near pass where tidal fields and gravitational waves exchange energy, yet the objects separate. It could mean capture into a binary that spirals inward over millions of years, with each orbit bleeding energy into space-time. Each case tests different rules, and each could fail for different reasons because the failure here is not mechanical. The failure would be logical, an inconsistency in how cause and effect are allowed to flow. Now we turn to the stranger half of the encounter, the half that exists more confidently on paper than in the sky. White holes appear when we time reverse a black hole solution, swapping infall for outflow in the geometry. If a black hole is a region nothing can escape, a white hole is a region nothing can enter. In the equations, it is a valid spacetime, complete with its own horizon and its own singularity in the past. In the universe, it is a rumour. In the maximally extended Schwarzschild geometry, the math includes more than one region, and it is often drawn as a Penrose diagram. There is a black hole region and, symmetrically, a white hole region. There are also two asymptotically flat exterior regions connected by an Einstein-Rosen bridge. This bridge is often called a wormhole, but it pinches off too quickly to traverse in classical relativity, closing before any signal could cross from one exterior to the other. Those diagrams can feel like a secret atlas of spacetime, with doors and corridors that ordinary intuition never visits. Yet that extended picture is not a proof of astrophysical white holes. It is a complete analytic extension of an idealized solution, not a formation story, and physics cares deeply about formation. Real black holes form from collapsing stars or from the growth of compact objects, not from eternal geometries that have always existed. Collapse creates an event horizon in one direction of time, not an outgoing horizon that ejects matter from a past singularity. The white hole region is allowed by the equations, yet it may be unreachable by realistic initial conditions. This is why white holes feel like mathematical ghosts, shapes implied by symmetry, but not summoned by known astrophysical processes. They are consistent with the field equations, but they have no confirmed observational footprint. No telescope has seen an object that only emits and never accretes, even when surrounded by gas. No survey has found a stable source that looks like time running backward at its boundary, with infalling matter mysteriously refused. The absence is not a disproof, but it is a warning about what nature seems willing to build. The warning becomes sharper when we ask about stability, because a white hole horizon is an anti-trap. Any small disturbance trying to fall in would be violently repelled in the time-reversed picture, and that repulsion is not gentle. In practice, that means the white hole may be hypersensitive to its environment, like a perfectly balanced pencil that cannot tolerate a breath of air. A single particle approaching the horizon could, in theory, trigger a catastrophic change of the spacetime, converting the white hole into something else. That something else might be a black hole, and the reasoning is almost cruelly practical. Many analyses suggest white holes cannot persist once they interact with ordinary matter, because the boundary conditions that define them are too fragile. The universe is not empty, and even deep intergalactic space has photons from the cosmic microwave background, neutrinos from ancient stars and drifting dust grains. If a white hole must remain perfectly isolated to exist, then existence becomes a fine-tuned miracle. The question shifts from what happens when they collide to can the white hole survive long enough to collide at all? Thermodynamics pushes the tension further, because horizons behave like statistical systems. Black holes obey laws that resemble the laws of heat, discovered in the 1970s when physicists noticed uncanny parallels. The area of an event horizon tends to increase, echoing entropy growth, and the surface gravity plays a role similar to temperature. Hawking's work sharpened this analogy by giving black holes a real temperature and an entropy proportional to horizon area, measured in units of the Planck scale. In this view, black holes are not just gravitational sinks, they are thermodynamic objects, with bookkeeping that seems to count hidden microstates. A white hole seems to run those laws backward, and that reversal is where the story becomes dangerous. If matter and radiation emerge from a white hole, the horizon area might decrease in the time-reverse story, as if entropy were being erased. Entropy would appear to drop, and the arrow of time would point the wrong way, at least locally. That is not merely counterintuitive. It threatens the statistical logic that underpins macroscopic physics, the same logic that makes broken cups stay broken. One response is that white holes are forbidden by the same reasoning that forbids unmixing cream from coffee. Possible in principle, but overwhelmingly unlikely in practice. The equations allow it, but typical states do not, and the universe lives in typical states. Another response is that a white hole could exist only as a rare fluctuation, brief and unstable, like an improbable eddy in a turbulent sea. A third response is that quantum gravity changes the bookkeeping, letting apparent entropy decrease locally while total entropy still rises. Each response implies a different outcome for a collision, because each changes whether a white hole can remain itself when confronted. So we return to the encounter itself, and we place it in the cleanest arena we can imagine. Picture a black hole and a white hole on a collision course, far from stars and gas, with only the thin fog of background radiation between them. The black hole's gravity pulls everything inward, including the white hole's outgoing streams, bending trajectories like a lens made of curvature. The white hole's boundary forbids entry, forcing trajectories outward, as if space-time were enforcing a strict one-way sign. Between them, space-time must decide which rule dominates, or whether both rules can coexist in a single consistent geometry. If the objects merge, what merges? Do two horizons combine into one, or do they annihilate into no horizon at all, leaving naked curvature exposed? Does the white hole's outgoing region become trapped behind the black hole's horizon, turning emission into accretion as the geometry reclassifies out as impossible? Or does the white hole inject energy and matter so violently that the black hole's horizon swells, radiates, or destabilizes, briefly breaking the calm predictability of Kerr? The collision is a test of causal structure, not just of force, and causality is the spine of the theory. Energy release is part of the stakes, but not the only one, because geometry can store and shed energy in unfamiliar ways. A merger could produce gravitational waves with an unfamiliar signature, since one partner would have reversed boundary conditions, changing how the horizon absorbs or reflects disturbances. A near pass could create bursts as outgoing material is lensed, shocked, or swallowed, producing flashes across the spectrum. In extreme scenarios, the interaction could create a transient wormhole-like geometry, or a region that resembles a cosmological bounce, where contraction gives way to expansion. These are speculative, but they define what we would look for, and they sharpen the difference between fantasy and testable prediction. The deepest stake is space-time stability, because general relativity is a theory of geometry responding to energy and momentum. If a white hole injects energy in a way that violates typical energy conditions, the geometry could behave strangely, and strangely here has technical meaning. Singularities could appear or disappear in ways the classical theorems did not anticipate. Horizons could form, split, or evaporate, changing what information can reach infinity. Causality could be threatened if closed time-like curves emerge in intermediate regions, turning the question into a paradox rather than a process. Yet we must be disciplined about what is known and what is imagined, because the two halves of this encounter do not share the same evidentiary weight. Black holes are supported by multiple lines of evidence, from stellar orbits around Sagittarius A to accretion physics in X-ray binaries, to gravitational waves from distant mergers. White holes are supported mainly by symmetry arguments and extensions of ideal solutions, plus occasional speculative proposals that remain unconfirmed. The collision question matters because it forces these two levels of confidence to meet. It asks whether our best-tested theory permits an encounter that our universe seems to avoid. This documentary follows that tension through 5 filters, each one narrowing the story without draining it of mystery. First, classical relativity asks what the field equations allow for horizons, boundary conditions, and mergers, when we take the mathematics at face value. Second, stability and entropy ask whether allowed solutions can persist against perturbations and the arrow of time, which is the universe's most consistent habit. Third, astrophysical reality asks what environments would do to any white hole candidate, long before a collision, because isolation is never perfect. Fourth, quantum gravity asks whether singularities, horizons, and time reversal are reshaped at the smallest scales, where space-time may have its own microstructure. Fifth, observation asks what signals could betray such an event, and how we would distinguish it from ordinary black hole behavior. Each filter narrows the space of possibilities, but it also clarifies what the question really is. Some paths end in a simple answer, where the white hole collapses into a black hole before contact, and the universe quietly restores the familiar one-way rule. Some paths end in a violent but conventional merger, where the black hole simply grows, and any exotic outflow is swallowed into the accounting of mass and spin. Some paths end in exotic transients, where outgoing matter meets an inescapable horizon and produces a unique burst, brief enough to be missed unless we know how to listen. And some paths end in contradictions, where the collision cannot be defined without breaking the assumptions of the model. The mystery is not only whether white holes exist, the mystery is what it would mean for time's direction to be negotiable at a horizon, even for an instant. Black holes taught us that gravity can hide information behind a boundary, and that the boundary itself behaves like a physical object in thermodynamic disguise. White holes would imply that information can be forced out, regardless of what tries to fall in, as if the universe were compelled to reveal what it normally conceals. Put them together, and we are really asking whether the universe can host two opposite one-way doors in the same hallway, and still keep its rules intact. We begin then by leaving imagination and entering the diagrams. The next step is to draw the one-way boundaries, track light cones, and see what approach even means when space-time itself is the arena. From there, we can ask the first hard question without flinching from what the equations imply. In classical relativity alone, is a black hole and white hole collision a permitted geometry or a forbidden story? Black holes are the known half of our impossible encounter, and they demand respect because they already bend intuition past its breaking point. They are not objects sitting in space like planets. They are regions where space-time's future points inward, so every allowed path leans the same way. In a black hole space-time, inward is not merely a direction on a map. It is a statement about causality, about which events can influence which other events, and which messages can never climb back out. If a white hole ever meets a black hole, the baseline must be solid, because the black hole side is the part we can test. So we begin with the physics of one-way worlds before we add the opposite one-way rule. We build the control case carefully, because exotic claims only become meaningful when ordinary expectations are sharp. In the darkness around a horizon, precision is not pedantry. It is the only light we have. A black hole forms when gravity overwhelms every pressure that can resist collapse, including the quantum pressures that normally keep matter stiff. In the simplest channel, a massive star exhausts nuclear fuel, and its core implodes, no longer supported by the outward push of fusion. The star's outer layers may explode as a supernova, but the core's fate is decided by what remains. As fusion ends, the core contracts and heats, and electrons are forced into protons through inverse beta decay, creating neutrons and a flood of neutrinos. For a time, neutron degeneracy pressure, quantum mechanics refusing to pack identical fermions into the same state, can hold the collapse. Yet if the remnant mass is high enough, even that last quantum scaffold fails, and the fall becomes unstoppable. In general relativity, the horizon forms outside the collapsing matter and then grows, enclosing a region from which no signal can return to distant observers. That detail matters, because it is not the singularity that announces itself first. What forms first is a causal boundary, a one-way membrane in the logic of space-time, and only later does the interior reach extreme curvature. Visualize the star's core as a shrinking sphere, its surface racing inward while the surrounding space-time tilts more steeply toward the center. Light cones, those diagrams that show what directions are possible for cause and effect, begin to lean. At a certain radius, the cones tip so far that outward is no longer a future direction, and the horizon is born. Stellar collapse is not the only route to a horizon, and the universe offers other pathways that are quieter, but no less profound. In the early universe, dense regions could have collapsed directly into primordial black holes, forming from radiation and matter fluctuations rather than from stars. Those objects, if they exist, would be fossils of the first second, tiny archives of inflation, reheating, and small-scale density structure. Primordial black holes are constrained by many observations, which is why they remain both tempting and elusive. Too many would distort the cosmic microwave background, disrupt nucleosynthesis, or overproduce gravitational lensing events. Yet the parameter space is wide, and in some models they range from asteroid mass to many solar masses, with narrow windows still open. If primordial black holes exist, they would not merely add another population of compact objects. They would change our story about what collapse means, because they would represent gravity acting before stars ever existed. That raises a quiet question. How early can the universe make a one-way world, and what does that imply about the initial conditions? There is also direct collapse in young galaxies, where gas clouds may avoid fragmenting into stars, and instead fall inward as a coherent massive flow. Fragmentation is usually the enemy of big seeds, because it turns a single collapsing cloud into many small stars. But if cooling and angular momentum loss cooperate through atomic hydrogen cooling, turbulence, and radiative feedback, a supermassive seed can form quickly. These seeds could explain billion solar mass quasars at high redshift, which shine when the universe is less than 1 billion years old. The timing is tight, and ordinary growth by steady accretion can struggle to reach those masses so fast. Direct collapse offers a shortcut, a way to start with a large black hole and then feed it. Once supermassive black holes exist, they also set the stage for frequent mergers as galaxies assemble. Galaxies do not grow in isolation. They collide, interpenetrate, and rearrange their stars like slow-motion storms. When two galactic nuclei meet, their central black holes are carried along, and the universe begins another long dance toward coalescence. Black holes come in broad mass families that guide every timescale and every signal, from milliseconds to millennia. Stellar mass holes are typically a few to tens of solar masses, with some heavier remnants now confirmed in gravitational wave catalogues. Intermediate mass candidates sit between about 100 and 100,000 solar masses, still debated and actively searched in clusters and dwarf galaxies. Supermassive black holes span millions to tens of billions of solar masses and anchor galactic centers, shaping stellar orbits and gas flows across light years. The mass scale sets the size of the horizon, because the Schwarzschild radius grows linearly with mass. A stellar black hole's horizon is the size of a city. A supermassive horizon can be larger than the orbit of Mercury. Mass is the first parameter, but spin is the second parameter that matters almost as much, because rotation changes the geometry itself. Real black holes are expected to rotate because their progenitors rotate, and because accretion carries angular momentum like a cosmic flywheel. Even a modest trickle of matter, arriving with a preferred direction, can torque a black hole over time. Typical stellar remnants may have moderate spins, though measurements vary by method and system, and the uncertainties are part of the story. X-ray binaries can suggest high spins through disk spectra and reflection features, but those inferences depend on modelling the disk's inner edge. Gravitational waves measure combinations of spins projected along the orbit, which are cleaner in some ways and limited in others. Supermassive spins reflect long accretion histories and merger histories, often inferred indirectly through jet power, disk efficiency, and the shape of broad iron lines. A black hole that grows by long, coherent accretion tends to spin up. A black hole that grows through many random mergers can end up with a more moderate spin, because angular momentum vectors cancel like tossed coins. In general relativity, an isolated settled black hole is described by the Kerr family, a solution found in 1963 that transformed the subject. It is specified by mass m and angular momentum j, plus charge in principle but negligible in astrophysics because plasma neutralizes charge quickly. This simplicity is startling. After collapse and settling, almost everything else is radiated away. We package spin into a dimensionless parameter array that equals Cj divided by gm squared, a number that compares rotation to gravity's ability to hold the horizon together. For a physical Kerr hole, A stays below 1 in classical theory, because exceeding it would remove the horizon and expose a naked singularity. That boundary is not just mathematical, it is tied to the cosmic censorship idea that nature hides its worst infinities. Kerr geometry changes the meaning of space and time near the horizon, and it does so in a way that feels almost mechanical when you see it visualized. Frame-dragging forces nearby matter and light to co-rotate, even if they try to resist, as though space-time itself is being twisted. The effect is tiny around Earth, but near a spinning black hole it becomes dominant. Outside the horizon sits the ergosphere, a region where no observer can remain stationary relative to distant stars because the dragging is too strong. In the ergosphere, standing still is not an option, which is a profound statement about what it means to be an observer. Inside that region, energy extraction is possible in principle, which makes spin a reservoir that can be tapped. The Penrose process was an early illustration of that reservoir, and it still serves as a conceptual beacon. A particle can enter the ergosphere and split, sending one fragment into the hole with negative energy relative to infinity, while the other escapes with extra energy. In modern astrophysics, magnetic fields provide a more practical mechanism, but the underlying idea is the same. Rotation can be mined. Spin also reshapes the inner edge of stable orbits around a black hole, and this is where geometry becomes observable. The innermost stable circular orbit depends on A, and on whether motion is prograde or retrograde relative to the spin. For a non-spinning hole, the ISCO sits at 6 gm/c² in Schwarzschild coordinates, a standard ruler in relativistic disk theory. For a rapidly spinning Kerr hole, the prograde ISCO moves inward, closer to the horizon, and the disk can radiate more efficiently because more gravitational binding energy is released. Retrograde orbits push the ISCO outward, reducing efficiency and changing the temperature profile of the inner disk. These are not small tweaks. They can change the brightness and spectrum of accreting systems. These details matter because mergers are not just two masses falling together like stones. They are two curved spacetimes exchanging energy, angular momentum, and multipole structure through gravitational waves, with the orbit acting like a transducer. The waves carry away not only energy but also information about the geometry that generated them. Spin-orbit coupling can tilt orbital planes and cause precession that imprints modulations in the waveform, like a wobble in the chirp's tone. Spin-spin effects and higher harmonics become important for accurate inference, especially when the masses are unequal or the spins are large. The waveform is a forensic record, but only if we model these relativistic couplings correctly. Black holes are expected to merge often because the universe builds structure hierarchically, assembling large systems from smaller ones. Galaxies collide and their central black holes sink toward a common center through dynamical friction, losing orbital energy to the surrounding stars and dark matter. The process is slow on human scales, yet inevitable on cosmic ones. In dense star clusters, repeated encounters harden binaries and drive compact objects together, because close interactions tend to eject lighter members and leave heavier pairs bound. Even in quieter environments, triple interactions can pump eccentricity and speed up coalescence, turning a long-in spiral into a sudden plunge. Nature has many ways to tighten a binary, and it uses them all. Before we discuss collisions, we must separate two ideas that are often conflated, because confusion here poisons everything downstream. The singularity is where classical curvature invariants diverge, and the theory signals its own breakdown, a warning label rather than a destination. The event horizon is a causal boundary that can be defined without reference to coordinates, and it is meaningful even when no local alarm rings. The horizon is physically meaningful because it divides what can influence distant observers from what cannot, and that division is operational. If you emit a flash of light outside the horizon, some observer far away can in principle detect it. If you emit the flash inside, no amount of engineering can make it arrive, because the future-directed paths all point deeper in. A horizon is not a surface you could scrape or dent, and it is not made of matter in any ordinary sense. Locally, a large black hole's horizon can be crossed without dramatic forces at that instant, because the curvature at the horizon can be small for large masses. What changes is global causal structure, which is why the boundary matters even when nothing special is felt. The singularity, by contrast, is not an object we can observe or model reliably with classical equations, and it is not a place where known physics remains trustworthy. Classical relativity predicts geodesic incompleteness, a failure of the spacetime description, and that is a clue that quantum gravity must intervene. Yet we do not know how, and the horizon blocks direct access. This distinction sets the rules for what we can know, and it also sets the rules for what stories can hide behind the horizon. From outside, we can infer mass, spin, and sometimes charge constraints through dynamics and radiation, because the exterior geometry shapes orbits and light paths. We cannot see the interior, and we cannot directly test what replaces the singularity, which is where speculation often gathers. Any white hole story will try to exploit that hidden region, so the boundary definitions must be clear and consistent. If the horizon is the one-way gate, then reversing it is not a small modification. It is a reversal of the causal arrows that define what later means for signals trying to escape. A qualified analogy helps, as long as we do not mistake it for the physics, because analogies can teach and mislead in the same breath. The rubber sheet picture suggests mass makes a dent that guides motion, but real gravity is curvature of space-time, not a force pulling through and embedding space. The analogy fails for time, which is the crucial dimension near a horizon. Still, it can anchor intuition about why trajectories converge and why freefall feels weightless even as the geometry tightens. In a better mental image, imagine light cones tipping as you approach the horizon, narrowing the set of future directions that lead outward. The horizon is where the outward pointing directions vanish, leaving only inward futures. Around many black holes, matter does not fall straight in, and the reason is as old as orbital motion itself. Gas forms an accretion disk because angular momentum prevents direct radial infall, forcing material into spiraling paths. The disk is not a rigid plate, it is a shearing, turbulent flow where neighbouring rings rub and exchange momentum. Turbulence and magnetic stresses transport angular momentum outward, letting mass drift inward, and the leading explanation is the magnetorotational instability. In plain terms, weak magnetic fields link fluid elements like springs, and differential rotation stretches those links until they drive turbulence. The disk heats by dissipation and can shine intensely in X-rays near the ISCO, where gravity's grip is strongest. In visuals, the disk is a bright, flattened whirlpool, its inner edge glowing white-blue while outer regions fade to red. Hotspots orbit at relativistic speeds, and their light is Doppler-boosted on the approaching side and dimmed on the receding side. Even without touching the horizon, the disk becomes a laboratory for strong gravity. Accretion adds complexity to any collision scenario, because it fills the space-time with matter that can radiate and shock. A black hole in a vacuum binary is a clean gravitational wave source with minimal electromagnetic emission, a near-ideal test of relativity. A black hole embedded in gas can produce shocks, flares, and variable jets that mask or mimic exotic signals. If we later claim a white hole signature, we must separate it from messy astrophysical environments where ordinary physics can already look strange. Gas can create time delays, spectral changes, and transient flashes that complicate interpretation. The challenge is not only detecting an anomaly, it is proving the anomaly is not just plasma behaving badly. Jets are the most dramatic example of that environment, and they turn rotation into spectacle across intergalactic distances. Many systems launch relativistic outflows aligned with the spin axis, likely powered by magnetic fields threading the horizon and inner disk. The Blandford-Znajek mechanism extracts rotational energy from a Kerr black hole through electromagnetic torques, converting spin into pointing flux. In the clearest images, jets appear as narrow beams that remain collimated for thousands of light years, ending in bright lobes where they crash into surrounding gas. Their radiation spans radio to gamma rays, and their variability can be rapid, implying compact emission regions near the black hole. Jets can dominate observed luminosity even when the accretion flow is dim, which is why some black holes announce themselves through motion rather than light. Now we set the baseline for a collision that we actually understand, at least in the sense that equations and simulations converge. In general relativity, a black hole merger proceeds through inspiral, plunge, merger, and ring down, a sequence that has become a new kind of astronomical narrative. Each stage has a characteristic timescale and a characteristic imprint on the gravitational waveform. During inspiral, the orbit shrinks slowly as gravitational waves carry away energy and angular momentum, and the binary behaves like a clock whose tick rate accelerates. The waveform chirps upward in frequency and amplitude as the separation decreases, with phase evolution that can be predicted using post-Newtonian expansions. Those predictions are not guesses. They are systematic approximations that match full simulations when used carefully. As the binary approaches the last stable orbit, the inspiral transitions to a rapid plunge, because stable circular motion is no longer available. The horizons distort, and a common horizon forms, enclosing both objects in a single trapped region, and that moment is a geometric event rather than a visible flash. The merger phase is highly nonlinear and is solved with numerical relativity, where supercomputers evolve Einstein's equations on a grid. Afterward, the remnant settles into a Kerr black hole through ringdown, shedding deformations as gravitational waves. Ringdown is the spacetime equivalent of a struck bell losing overtones, but the bell is geometry itself. The remnant emits quasi-normal modes whose frequencies and damping times depend mainly on M and AOs, because those parameters define the final Kerr spacetime. Measuring multiple modes tests the no-hair expectation that the final state is Kerr, and it is one of the cleanest strong field tests we can imagine. Any deviation in mode content or damping could signal new physics or an unusual boundary condition, including partial reflection near the horizon. The question is subtle. Are we seeing a new object, or are we seeing an old object in a new environment? A key quantitative anchor is the energy budget, because it tells us how violent the event really is. Typical stellar mass mergers radiate a few % of the total mass energy as gravitational waves, which is an almost absurd conversion efficiency. That energy leaves as pure space-time curvature, not as light, and it can briefly outshine all stars in the observable universe in gravitational luminosity. The remnant mass and spin are reduced accordingly, and the final spin is often around 0.7 for comparable mass, non-extreme configurations. In simulations, the horizon area increases, consistent with the area theorem under reasonable energy conditions, and the system's entropy rises. Even without mentioning thermodynamics, the mathematics already points toward irreversibility. Mergers can also kick the remnant through asymmetric radiation, a recoil that is as real as a gun's kickback. If masses are unequal or spins are misaligned, gravitational waves carry net linear momentum, and the remnant must recoil to conserve momentum. The recoil can reach hundreds to thousands of kilometers per second in extreme configurations, fast enough to roam within a galaxy or escape a small one. In galaxies, that can displace a supermassive remnant or even eject it from shallow potential wells, leaving a nucleus temporarily without its anchor. Such kicks could affect how quickly black holes grow, how often they merge again, and where we should search for wandering massive black holes. The universe may be littered with exiles, moving through halos with little to betray them. These are not abstract predictions anymore, and that shift from theory to catalogue is one of the quiet revolutions of modern astronomy. LIGO and Virgo have detected dozens of black hole mergers, and CAGRA adds global sensitivity and sky localization, turning a two-detector experiment into a network. From the chirp, we infer component masses, effective spin, and distance with model-dependent uncertainties. We also test consistency between inspiral and ring-down, which probes strong field gravity by comparing early and late parts of the same event. The inspiral encodes the binary's parameters before merger, while the ring-down encodes the remnant's parameters after merger. If the two disagree beyond uncertainties, something in our assumptions is wrong, either the astrophysics, the modelling, or the theory. For supermassive black holes, the evidence is different but equally compelling, built from patient observation rather than millisecond chirps. Stellar orbits around Sagittarius A trace a compact mass of about 4 million solar masses within a tiny volume, and the stars move so fast that relativistic corrections are measurable. The centre is dark, invisible light, yet gravity reveals what light cannot. In M87 and our own galaxy, the Event Horizon Telescope images show a bright ring and central shadow consistent with light bending near a horizon. The ring is not the horizon itself, it is a lensed photon orbit region, where light can loop around before escaping. These observations constrain mass and geometry, though they still do not reveal the interior because the shadow is a silhouette cast by space-time. Across these scales, the same lesson repeats, and repetition here is not redundancy, but reinforcement. We can map the exterior space-time and measure parameters that define Kerr, sometimes with astonishing precision. We cannot directly observe the horizon as a material surface, and we cannot see what happens beyond it, because the boundary is defined by what cannot be seen. The interior remains hidden, which is why exotic alternatives often hide there, proposing modifications where observation cannot easily reach. Yet the exterior is not infinitely flexible, and many alternatives are constrained by how well Kerr fits real data. The challenge is to find a deviation that is both physically plausible and observationally distinguishable. This baseline also tells us what a normal collision should look like, and why deviations are so valuable. If a hypothetical white hole behaved like another compact object with similar mass and spin, the gravitational waveform would resemble a standard binary signal. The inspiral would follow post-Newtonian predictions, then plunge and ring down would match Kerr within the usual uncertainties. Any systematic deviation becomes the clue that one partner is not a standard horizon, and that clue must survive cross-checks. It must appear in multiple events, or in multiple parts of the waveform, or in a way that cannot be tuned away by changing masses and spins. Otherwise, it is just a mirage created by noise or imperfect modelling. To make that statement meaningful, we need to say what the horizon does during a merger, because the horizon is not passive. In classical GR, a black hole horizon absorbs perturbations and grows in area, consistent with the area theorem under reasonable energy conditions. It is not a perfect mirror, though it can reflect in some effective descriptions with modified boundary conditions, and those differences matter in principle. The absorption affects phase evolution slightly, especially for high spins and close orbits, because energy can flow into the horizons as well as out to infinity. In waveform language, the horizon acts like a sink that damps certain modes, adding a subtle dissipation channel. That channel is small but calculable, which is exactly the kind of detail an exotic object would disrupt. The horizon also sets a one-way condition for information flow, and that is the deepest part of the baseline. Signals can fall in and never return to infinity, which makes the exterior evolution appear dissipative, even though the full space-time evolution is deterministic in classical GR. The one-way character is not a force. It is a constraint on which world lines can connect which events. This is why ring-down decays, and why the remnant approaches Kerr, because perturbations are either radiated away or swallowed. If the horizon were replaced by a reflective surface, some perturbations could bounce back out and create late-time echoes. Whether such echoes exist is an observational question, but the baseline tells us what no echoes should look like. We should also acknowledge what we do not yet know cleanly, because the horizon is not only geometry, it is also thermodynamics. The information paradox and Hawking radiation indicate that quantum effects matter for ultimate accounting, even if they are tiny in everyday astrophysical contexts. Hawking's calculation assigns a temperature to the horizon, and that temperature is inversely proportional to mass, making large black holes extremely cold. For astrophysical timescales, Hawking evaporation is negligible for stellar and supermassive holes, so it does not change merger dynamics in any practical way. Still, the paradox reminds us that horizons are not merely geometric, they are also quantum mechanical bookkeeping devices. If a white hole is ever to be more than a metaphor, it must contend with that bookkeeping. There is historical weight behind these ideas, and it helps to remember how recently they became physical rather than philosophical. The term black hole was popularized in the late 1960s, but the solutions were older and the debates were fierce. For decades, the horizon was treated as a coordinate artifact by some, until global definitions and collapse models made its reality unavoidable. Numerical relativity, too, was once a dream rather than a tool, because evolving Einstein's equations stably is notoriously difficult. Only in the 2000s did stable merger simulations become routine, and only then did waveform templates become accurate enough for detection. When LIGO first observed a chirp in 2015, it was not just a discovery of mergers, it was a confirmation that our baseline calculations were finally mature. For this chapter, we keep the focus on the classical and observational foundation, because it is the foundation any reversal must challenge. Black holes form through multiple channels that are plausible in real cosmic history, from stellar death to early universe collapse to galactic-scale inflows. They merge frequently in dense environments and during galaxy growth, and their exterior is well described by Kerr. Their mergers produce predictable gravitational wave signatures, and those signatures have been observed, modelled, and cross-validated across instruments. That does not mean the story is complete, but it does mean we have a working grammar for one-way worlds. Without that grammar, the word white hole would be only an aesthetic contrast. So what does collision mean in our question? In the black hole baseline, collision means a common horizon forms and the system relaxes to Kerr, with no material surface to strike and no rebound to watch. The observable is a chirp followed by ring down, plus possible electromagnetic activity if gas is present, and the details depend on masses, spins, and orientation. The interior remains causally disconnected from us, which is part of what makes the baseline robust, because it limits what can complicate the signal. We do not have to model nuclear matter at a surface, because there is no surface. We do not have to model elasticity, because the horizon is not a substance, and that simplicity is a gift. This robustness is exactly why the white hole idea is so disruptive, because it would rewrite the boundary condition that makes black holes simple. A white hole would reverse the horizon's role, turning a sink into a source, and flipping the direction of allowed causal flow. If such an object entered a binary, would the inspiral still look like Kerr plus Kerr, or would the phase and damping change in a measurable way? Would ring-down still be a clean set of quasi-normal modes, or would it be contaminated by reflection and outflow, adding structure where we expect smooth decay? Would the remnant settle quickly, or would it keep talking through late-time features that standard horizons silence? And if a white hole can expel matter and radiation, what would that do to the surrounding disk, the jet, and the timing of any flare? We begin then by locking in what black holes do when they meet each other, because that is the control experiment written in space-time. Only then can we ask what happens when one partner refuses to be a one-way sink, and whether that refusal can be seen at cosmological distances. Black holes are stable endpoints of collapse, so what would a white hole be the endpoint of, and why do we not see them? Somewhere in the dark between galaxies, our hook returns with sharper edges, as if the universe itself has honed the idea. A black hole only swallows, and its reputation comes from that one-way accounting of light and matter. A white hole would only release, and that reversal feels like a dare aimed at everything we trust. If they ever collide, the outcome depends on whether white holes can persist, whether the cosmos allows a one-way exit to remain open. We begin then by leaving imagination and entering the diagrams. White holes are not invented to be spooky, even if the name sounds like folklore. They appear when general relativity's exact solutions are extended and then time reversed, with the mathematics kept perfectly intact. In Einstein's field equations, time does not carry an intrinsic moral direction. It is the boundary conditions that decide what actually happens. In general relativity, a white hole is the time reverse of a black hole, defined by what can and cannot cross its horizon. Nothing can enter it from the outside, not even a photon aimed with perfect precision. Matter and light can emerge from its horizon and escape outward, as though space itself is exhaling. The reversal is clean in the equations, but it is unsettling in the world. That definition is not about a hard surface, like a planet's crust or a star's photosphere. It is about causal structure, about which events can influence which other events through signals moving at or below light speed. The horizon sets which world lines can cross and which signals can connect events, and it does so without needing any physical wall. You can fall through a horizon without feeling it locally, and that is part of the strangeness. To make this accessible, we use causal diagrams without drowning in jargon, because the jargon can hide the simple idea. A Penrose diagram compresses infinite distances into a finite picture, like folding an endless road into a postcard. It keeps light rays at 45 degrees so causality stays visible, and so, can this affect that becomes a geometric question. In these diagrams, the drama is drawn, not acted. In that picture, a black hole horizon is a boundary you can cross inward, but never outward, once you have committed. A white hole horizon is the opposite boundary, drawn with the same elegance but a different arrow. You can cross outward from inside, but never inward from outside, no matter how long you wait. The rule is not about force, it is about the structure of space-time itself. This is why white holes feel like shadows of black holes, cast by the same object under a reversed light. They are built by reversing the direction of time in a known geometry, like running a film backward without changing any frames. The equations remain satisfied, but the story of formation changes completely, and that story is where physics usually lives. We can write the solution, yet still doubt the universe will stage it. The cleanest place to see the symmetry is the maximally extended Schwarzschild spacetime, which is a kind of mathematical cathedral. It is the eternal, non-spinning, uncharged solution, extended as far as mathematics allows, with every corridor opened. It contains more regions than a collapsing star ever reveals, because it assumes the spacetime has always existed. Historically, this extension became clear through coordinate work by people like Eddington, Finkelstein, Kruskal and Sikaris, who showed that the horizon is not a true singularity. In the standard labeling, region 1 is an exterior universe where far away looks flat, and clocks behave normally by local standards. Region 2 is the black hole interior, where future directed paths head to a singularity, not by choice but by geometry. Region 3 is a second exterior region, disconnected in ordinary coordinates, like a mirror universe that appears only when the map is complete. The diagram is compact, but it encodes an entire causal architecture. Region 4 is the white hole interior, where the singularity sits in the past rather than the future. From that past singularity, world lines emerge and move outward, as though the universe is ejecting matter from an origin it refuses to explain. The white hole horizon is the boundary that prevents outside entry, and it does so globally, not by any local repulsion. In the diagram, the past seems to leak into the present. The diagram also includes a bridge between the two exterior regions, drawn as a narrow throat connecting wide spaces. This is the Einstein-Rosen bridge, often called a wormhole in popular language, though the popular word carries extra promises. In classical general relativity, it is not traversable, and that limitation is not a matter of engineering. It is a statement about how the geometry evolves. The reason is geometric, not technological, and it is almost cruel in its simplicity. The bridge pinches off too quickly for any signal to cross from one exterior to the other, even if the signal is light. By the time you try to traverse, the throat has already closed, and the attempt becomes a fall into region 2. The bridge exists on the diagram, yet it refuses to function as a tunnel. This matters for our collision question because it separates mathematics from astrophysics with a sharp line. The maximally extended solution is an eternal space-time, not a realistic formation history, and nature cares about histories. Real black holes form from collapse, and collapse does not naturally produce region 4, because collapse has a beginning in time. The extension is a map of possibilities, not a record of events. In gravitational collapse, the horizon forms and grows around infalling matter, and the outside world sees that growth slowed by time dilation. The interior is a future singularity in the classical picture, reached in finite proper time by infalling observers. There is no past singularity ejecting matter into the exterior, and there is no need for one. The star dies forward in time, not backward. So the white hole region is not a predicted outcome of ordinary stellar death, even if the equations allow it in principle. It is a permitted region of an idealized extension, the way a chessboard permits moves that never occur in a real game. The difference sounds technical, but it is the difference between a map and a road, and between a theorem and a sky. A universe can be mathematically consistent and still physically implausible. If white holes are not formed by collapse, how could they exist at all without smuggling in miracles? One answer is that they could be primordial, built into initial conditions like a rare feature in the earlier space-time fabric. Another answer is that they could be quantum remnants of black holes, created by a bounce rather than an end. Both answers lean heavily on what we do not yet know about the earliest moments and the deepest densities. Before we chase loopholes, we confront the central obstacle, because it is the obstacle that shapes everything else. White holes look allowed mathematically yet disallowed physically, and that tension is the heart of the mystery. The disallowing force is not a single theorem, but a convergence of stability and entropy arguments that all point the same way. When different lines of reasoning agree, physics starts to feel less negotiable. Thermodynamics enters because horizons behave like thermodynamic systems, even though they are made of geometry rather than atoms. In classical general relativity, Hawking's area theorem says black hole horizon area does not decrease, assuming reasonable energy conditions and the absence of exotic matter. The area behaves like an entropy proxy, a measure of hidden information that only grows. It is as if the universe keeps a ledger at the horizon. Then Hawking radiation and black hole thermodynamics make the analogy literal, and the ledger becomes a law. The Baconstein, Hawking entropy is proportional to horizon area, and the proportionality is astonishingly simple. In units where constants are set appropriately, S is about A divided by 4, with the Planck area setting the scale. The formula is compact, yet it hints at microscopic degrees of freedom we cannot directly see. This is not a decorative formula, and it is not merely a clever coincidence. It ties geometry to microphysical counting, even if we do not yet know the microstates, and it ties black holes to the second law of thermodynamics. A horizon becomes a thermodynamic object, with temperature, entropy, and a kind of statistical inevitability. The black hole is no longer just a gravitational trap. It is a thermodynamic system. In the generalized second law, ordinary entropy outside plus black hole entropy tends to increase, even when horizons complicate the accounting. When matter falls in, the outside entropy can drop, but the horizon area grows to compensate, and the total tends to rise. The bookkeeping stays one way, and that one-way behavior matches our lived experience of time. We remember the past because entropy increased, not because equations demanded memory. A white hole seems to demand the opposite bookkeeping, and that is where it begins to feel like an outlaw. If matter and radiation emerge, the horizon area in the time reverse picture would shrink, reversing the classical area trend. That looks like entropy decreasing, which clashes with the observed arrow of time and with the statistical behavior of macroscopic systems. The white hole is not just rare, it is antitypical. One can say the second law is statistical, not absolute, and that is true in the technical sense. A decrease is not forbidden, only fantastically unlikely for macroscopic systems, like a shattered glass reassembling itself mid-air. That reply helps mathematically, but it makes white holes into extreme fine-tuned exceptions, not natural outcomes. The universe would have to roll an impossible number of favourable dice and do it consistently. To get a macroscopic white hole, you need a macroscopic entropy miracle, not just a microscopic fluctuation. You need the universe arranged so that an enormous number of degrees of freedom converge into a special low-entropy boundary condition and keep it stable. The white hole becomes a demand on the past, because the past must be arranged to make the future emission clean. It is less an object than a conspiracy of initial data. This is where the phrase prearranged ejection earns its weight, because it captures the hidden cost. A white hole is not merely an object that emits, like a star radiating heat. It is an object whose entire past must be coordinated so that emission occurs without any allowed infall and without the usual entropy growth. The more massive the white hole, the more extravagant the coordination becomes. Cosmic censorship enters as a guiding suspicion, not a settled verdict, and it hovers like a warning sign. The conjecture says singularities produced by realistic collapse are hidden behind horizons, protecting distant observers from naked breakdowns of physics. White holes invert that story by placing a singularity in the past that influences the exterior, at least indirectly through emitted matter. The conjecture is not proven, yet it expresses a deep expectation about what nature tends to hide. To have that past singularity without a collapse history, you must specify initial data on a past boundary that is exquisitely tuned, down to details we usually treat as irrelevant noise. Any generic perturbation in the past would spoil the clean white hole region, because the horizon's one-way rule is global. The universe would have to start with a trapdoor already open, and with every gust of randomness somehow cancelled. The requirement is not just special, it is structurally special. Even if we grant such initial conditions, stability becomes the next barrier, and it is a barrier that does not negotiate. A white hole horizon is widely argued to be unstable to perturbations, and the argument is tied to how fields behave near horizons when traced backward in time. What is gentle in one direction becomes violent in the other, because horizons stretch and squeeze frequencies. The same geometry that redshifts can, under reversal, blue shift. The key idea is blue shift, and it is easier to feel than to formalize. Near a horizon, outgoing light seen by distant observers is redshifted, its frequency drained as it climbs out of a gravitational well. In the time-reverse situation, what looks like a gentle background field can become violently blue-shifted at the horizon, concentrating energy into a thin region. A whisper becomes a scream when played backward through space-time. For a white hole, tiny incoming radiation from the outside is not supposed to enter, and that is the rule we keep repeating. But the horizon is a global boundary, not a local shield, and physics is rarely kind to global rules. Perturbations hovering near it can be amplified in the backward time sense, producing enormous effective energy densities that distort the geometry. The horizon becomes a place where small imperfections are magnified. This makes the white hole hypersensitive to the environment, and the environment is never truly quiet. Even a small amount of infalling matter, or even a stray photon, can destabilize the horizon structure, at least in many analyses. The ideal white hole is like a perfect mirror that cannot tolerate dust, and the universe is dusty in ways that are easy to underestimate. The problem is not dramatic collisions, it is persistent background. In a real universe, there is always dust and there is always radiation, even where it looks empty. Even in intergalactic voids, the cosmic microwave background fills space with photons at a few Kelvin, arriving from every direction. There are also neutrinos from the early universe, and gravitational waves from distant mergers, passing through like faint ripples. The vacuum is a stage with constant low-level noise. Those backgrounds are weak in everyday terms, but the white hole's problem is not strength, and that is the twist. The problem is that the horizon condition is absolute, and it must remain absolute for the definition to hold. If the condition is even slightly violated, the geometry can reconfigure into a black hole, because the black hole is the stable attractor in this thermodynamic landscape. The universe tends to settle into the direction that absorbs, not the direction that emits. So the phrase "poisoned instantly" is not just rhetoric, even if it sounds dramatic. A realistic environment provides a steady drizzle of perturbations, and the white hole would have to repel them perfectly forever. If it fails, even briefly, the one-way boundary can flip into the more stable one-way world, and the white hole becomes what it was meant to oppose, the instability is not a slow leak, it is a structural vulnerability. We should state the likely outcome clearly, because clarity is part of the suspense. Many analyses suggest that any realistic white hole would rapidly become a black hole once it interacts, because interaction is unavoidable. The time reverse of a stable absorber is not a stable emitter in a noisy universe, and noise is the default state of reality. Time symmetry in equations does not guarantee time symmetry in behavior. This is the suspense point of the chapter, and it is a deep one. White holes sit at the intersection of symmetry and irreversibility, where our neat mathematical instincts meet messy statistical facts. General relativity's equations are time-symmetric in form, but the solutions we see in nature are not time-symmetric in practice, because the universe began in a low-entropy state. The arrow of time is not a line in the equations, it is a condition of the cosmos. The arrow of time is not written into Einstein's equations directly, and that absence is almost philosophical. It emerges from boundary conditions and entropy, from the initial state of the universe and the way probabilities flow. White holes force us to ask whether the arrow is merely a habit of our universe, or a deeper constraint that selects which solutions are realized. If the equations permit a reversal, why does the universe refuse to perform it? Now we connect this back to the collision question without jumping ahead, because the collision is our narrative magnet. If white holes are unstable, then a black hole and white hole collision becomes a race, not a simple encounter. Does the white hole survive long enough to meet its opposite, or does it decay into a black hole long before the orbit tightens? The outcome depends on which clock runs faster, orbital dynamics or horizon instability. To answer that race, we need a rough hierarchy of timescales, the kind of hierarchy that decides what is relevant. A binary and spiral can take millions to billions of years if it starts wide, because gravitational radiation is a weak drain at large separations. Even a close encounter can take many orbits to merge if gravitational radiation is the only sink, and if there is no surrounding gas to accelerate the process. The sky's great dances are often slow. A white hole instability, by contrast, could be immediate once perturbations accumulate near the horizon, because the amplification is geometric. If the instability timescale is shorter than the orbital timescale, the collision never happens as advertised. The system becomes black hole plus black hole long before contact, and the exotic partner vanishes into the ordinary. In that case, the collision is a story that cannot be staged, but we cannot stop at the simplest dismissal, because physics often hides surprises in the corners. Some proposals try to rescue white holes by changing the interior physics, where classical general relativity is expected to fail. These proposals do not claim classical white holes are common, and they do not claim the maximally extended diagram is an astrophysical blueprint. They claim quantum gravity might produce white hole-like phases, briefly and under extreme conditions. One family of ideas is bounce models, and the word bounce is doing a lot of work. Instead of a singularity, collapsing matter reaches a high-density regime and rebounds, as if spacetime develops an effective stiffness. The rebound could connect a black hole interior to a white hole interior across a quantum region, replacing the classical end with a quantum transition. The singularity becomes a placeholder for unknown physics. Loop quantum gravity has inspired specific versions of this story, and it does so by quantizing geometry itself. In some models, quantum geometry generates an effective pressure that halts collapse, even when classical gravity would be relentless. The black hole could transition into a white hole over a long external time, because time dilation stretches the process for distant observers. What is quick inside can be slow outside. The term Planck star is often used in this context, and it evokes an object at the edge of meaning. The idea is that the core reaches Planck density and then expands, not as a conventional explosion, but as a quantum gravity-regulated release. Due to gravitational time dilation, the bounce could be quick internally but slow as seen from far away, like a flash trapped behind a thick glass wall. The outside waits while the inside evolves. These models attempt to reconcile time symmetry with the observed arrow of time, and they do it with careful bookkeeping. They try to keep global entropy increasing while allowing a local reversal inside the horizon, where information is hidden from the exterior. They also try to replace the singularity with a unitary evolution, so that quantum information is not destroyed. The hope is that the universe remains lawful even at its deepest extremes. Yet they face their own constraints, and those constraints are not merely aesthetic. The transition must avoid producing observable contradictions with known black hole behaviour, including the long-lived darkness of many astrophysical holes. It must not create frequent bright explosions that we would already have catalogued across the electromagnetic spectrum. If the sky would be flashing with these events, we would likely have noticed. It also must confront the same environment problem in a new form, because the exterior does not pause. If a black hole transitions to a white hole, the exterior is not empty, and it is often busy with accreting matter. The hole is surrounded by radiation, magnetic fields, and sometimes a disk of plasma, which could choke any emerging phase or smear it into a more ordinary flare. The white hole-like moment would have to push through a crowded neighbourhood, so even the quantum loopholes do not guarantee a stable, long-lived white hole in open space, and that is an important restraint. They suggest a transient event, perhaps delayed, perhaps rare, perhaps conditioned on isolation. They shift the question from object to process, and that shift changes what we should look for. A process leaves a signature, not a permanent landmark. That shift matters for observation, because astronomy is often the art of catching brief changes. If white holes are brief, we should look for transients rather than steady emitters, and we should be careful about what brief means at cosmic scales. The sky is full of fast, bright events, and some have been loosely connected to white hole speculation, often because they seem to release energy abruptly. But abruptness alone is not a fingerprint. Fast radio bursts are one example often mentioned, partly because they are so short and so intense. They are millisecond radio flashes with enormous inferred energies, and their distances place them in other galaxies. Their origins are still debated, though magnetars and plasma processes explain many features, including repeating sources and polarization signatures. The temptation to invoke white holes often arises when the mechanism feels too compact for the energy. Gamma-ray bursts are another example sometimes invoked, because they are among the most luminous electromagnetic events known. Yet most GRBs have strong evidence for massive star collapse or compact binary mergers, and many show afterglows consistent with relativistic jets. When the data points to known engines, exotic explanations become unnecessary. Still, the sheer violence of GRBs keeps them in the conversation as a benchmark of what nature can do. There are also unusual transients that do not fit neat categories, and the catalogues keep growing. Some are fast blue optical transients, some are orphan afterglows, some are radio flares without clear hosts, and some are events with puzzling environments. The temptation is to label the unknown as exotic, because the unknown feels like an invitation. But the history of astronomy teaches caution, because the mundane often arrives late. We must emphasize the difference between hypothesis and evidence, because the documentary tone depends on honesty. A white hole interpretation is usually not required by the data, and it rarely provides unique predictions. At best, it is one story among many, and often it is the least constrained story because it can be tuned to fit. The burden is not to imagine, it is to discriminate. Still, these speculations serve a purpose for our documentary, and the purpose is not to declare victory. They define what a white hole-like event might look like if it existed, and they clarify what would count as a distinctive signature. They also force us to think about what horizons do, and how boundary conditions might leak into observables. Even a wrong idea can sharpen the right questions. A key signature would be an outflow without an obvious engine, especially if the environment looks empty and old. Another would be a burst that appears to come from an isolated region with no star formation, where magnetospheres and massive stars are scarce. Another would be a transient with an unusual time profile that suggests delayed release, as though energy was stored and then suddenly allowed out. Each of these hints at something hidden behind a horizon. Yet even these are not unique, and that is the practical frustration. Black hole accretion can flare, especially when magnetic fields reconnect or disks become unstable. Magnetars can burst, and their magnetospheres can produce complex repeating behavior. Relativistic shocks can mimic almost any light curve if parameters are tuned, and astrophysics has many parameters. The universe can look exotic while remaining conventional, so the observational status remains cautious, and it should remain cautious. White holes are not confirmed astrophysical objects, and no event demands them as the best explanation. The best we can say is that some quantum gravity ideas motivate looking for rare explosive releases, and the sky provides many candidates that still need explanation. The mystery is real, even if the label is uncertain. Now we return to the causal diagrams because they anchor the collision logic with clean geometry. In a Penrose diagram, the white hole region is separated from the exterior by a past horizon, which is a boundary defined by what cannot enter. The black hole region is separated by a future horizon, defined by what cannot escape. These are not just lines on paper, they are statements about the reach of cause and effect. If we imagine bringing a black hole and a white hole together, we are really imagining bringing two different horizon boundary conditions into one spacetime, and that is a delicate thought. One boundary absorbs and hides, turning incoming information into inaccessible interior data. The other boundary emits and forbids entry, turning the interior into a source rather than a sink. The clash is not simply gravitational, it is causal. In classical general relativity, horizons are not material membranes that can collide like shells, and this is where language starts to strain. They are global features determined by the entire future of spacetime, which means you cannot define them fully without knowing what happens later. That makes the phrase collision subtle and, in a way, ominous, because the geometry decides what the horizons even are. The event horizon is a verdict delivered by the future. A black hole horizon can grow when it absorbs energy, and this growth is tied to the area theorem and to entropy. A white hole horizon in the time-reversed picture would shrink as it emits, and that shrinkage is thermodynamically suspicious. Put them near each other, and the global definition of each horizon may change, because the space-time is no longer isolated. The boundaries can warp, merge, or disappear depending on the full evolution. This is where the arrow of time becomes operational, not philosophical, because the accounting becomes physical. If the white hole emits into the black hole's gravitational field, much of that emission could be captured, especially if the objects are close. The black hole horizon would grow, increasing area and entropy, and the combined system would look more ordinary with time. The universe would be doing what it statistically prefers. From the outside, the white hole could look like a brief outburst that is quickly swallowed, like a flare that dies as it rises. The combined system could settle into an ordinary black hole, with the white hole phase erased by absorption and by horizon redefinition. The universe would choose the stable direction, and the time-reversed boundary would be overwritten. The symmetry would exist only in the equations, not in the outcome. But we should keep the alternative alive for suspense, because the alternative is where signals might hide. If the white hole emission is intense and asymmetric, it could perturb the black hole strongly, injecting energy and momentum in a lopsided way. It could drive gravitational waves with unusual mode content, because the boundary conditions differ from pure absorption. The waveform could carry a subtle imprint of a horizon that behaves differently. In a merger, black hole horizons act like sinks that damp perturbations, and the ring down is a kind of gravitational settling. A white hole horizon would act like an anti-sink in the time-reversed sense, potentially amplifying certain disturbances rather than damping them. That could alter in spiral phasing and ring-down damping, shifting how quickly the system forgets its initial state. The difference would be encoded in decay times and spectral content. This is not a promise of a spectacular signal, and it is not an invitation to overclaim. It is a statement that the waveform could encode boundary conditions, because gravitational waves are sensitive to how spacetime responds. If a horizon reflects or emits rather than absorbs, the gravitational response changes, and the change could be measurable in principle. The challenge is that in principle is not the same as in data, yet the stability arguments keep pushing us back, and they do so with the stubbornness of thermodynamics. In a universe filled with background radiation, the white hole may not remain a clean boundary long enough, especially during a close approach. The same blue shift logic that destabilizes it would operate during approach, when fields are distorted and focused. The closer the encounter, the harsher the environment becomes. Even if the white hole begins in a pristine vacuum, the black hole's tidal field and gravitational focusing could funnel ambient radiation toward the white hole horizon, concentrating the very noise it cannot tolerate. The approach itself could accelerate the poisoning, because trajectories that would have missed are bent inward. The collision could be prevented by the attempt to collide, as if proximity triggers the collapse into normalcy. The universe resists the setup. This is the chapter's core tension, and it is the tension we carry forward. The mathematics offers a symmetric partner to the black hole, drawn with the same lines and the same elegance. The physics of entropy and perturbations makes that partner fragile, perhaps impossible, in any realistic setting where noise exists. The question becomes not can we write it, but can it survive? So what do we take forward into the next chapters without pretending we have solved the riddle? We take forward a careful definition, a map of regions, and a list of failure modes that are grounded in known physics. We also take forward a narrow window where white holes might appear as brief quantum transitions, more event than object. That window is small, but it is not empty. We end by tightening the central question rather than answering it, because the next step is dynamics. If a white hole is a time-reverse shadow, then it fights the universe's arrow of time at every moment, and every photon in the background becomes a threat. If it is unstable, then the collision becomes a timing problem, not just a geometry problem, and timing is the language of astrophysics. The universe may not forbid the idea, yet it may refuse the performance. Transition. If white holes are unstable in a messy universe, then a collision with a black hole becomes a question of timescales. Does the white hole survive long enough to meet its opposite, or does it become the thing it was meant to defy? Next, we follow that question into dynamics, where horizons are forced into shared space-time and definitions begin to shift. We ask what signals would escape and what rules would break first, if any rule can break at all. We have a paradox with teeth, but paradox alone never makes an event because nature still demands a pathway. Even if a white hole can exist in principle, we still must engineer a meeting with a black hole. This chapter sets the trap in astrophysical terms and asks whether the universe permits it. A meeting sounds simple until you remember what meeting means in general relativity, where geometry outranks intuition. In curved space-time, objects do not merely approach through space, they approach through causal structure, through horizons, and through the bookkeeping of energy and entropy. The camera can show 2 points spiraling together, but the physics asks a colder question. Can their boundary conditions coexist long enough to matter? First, we define collision, because the word hides 3 different stories that look similar from far away. One meaning is a horizon merger, where a common trapped region forms and then settles into a final remnant. A second meaning is a close encounter with mass transfer, where outflow meets inflow without immediate horizon union. A third meaning is a white hole ejection event that happens near an existing black hole, with proximity shaping what escapes. Each definition implies a different observable and a different failure mode, which is why we cannot treat them as synonyms. A horizon merger demands that both horizons persist long enough to share space-time, even as tidal fields and radiation try to destabilize them. A mass transfer flyby demands that the white hole can emit without instantly collapsing into an ordinary absorber under perturbation. A nearby ejection demands only a brief white hole phase, not a long-lived object, yet it must still be timed to occur near a black hole. These are not semantic games, because horizons are not material surfaces you can touch or dent with a probe. An event horizon is a global feature of space-time, defined by which light rays can reach infinity and which cannot. That global definition makes contact slippery. 2 horizons can influence each other long before any common horizon is said to form. In practice, we often use apparent horizons in simulations because they are locally defined and trackable during dynamical evolution. So our 3 collisions are really 3 space-time histories, each with its own causal logic and its own thermodynamic accounting. A merger story asks how trapped regions join, while a flyby story asks how energy flows without a shared trap. A nearby ejection story asks how a transient boundary condition imprints itself on what distant observers can actually measure. The trap is not just spatial, it is a trap of definitions. Now we move from diagrams to formation channels because orbits need origins. Black hole binaries form through stellar evolution, through dynamical capture, and through hierarchical assembly in galaxies. If white holes exist, they must enter one of those channels or create a new one. Either way, the universe must supply not only an object, but also a clock that brings it close. The cleanest astrophysical pathway is a bound binary, because binaries naturally merge once dissipation has done its work. In isolated stellar binaries, common envelope evolution can shrink separations dramatically, turning wide pairs into compact engines. A giant star engulfs its companion, drag removes orbital energy, and the core separation tightens as angular momentum is redistributed into the envelope. After envelope ejection, 2 compact remnants can remain in a close orbit. Visually, common envelope evolution is not a gentle dance, and it rarely looks symmetric from any angle. It is a plunge into a swollen atmosphere, where friction heats gas into turbulence, and spiral shocks wrap around the cores. The envelope can glow, expand, and then tear away in clumpy arcs, leaving behind a stripped core and a compact companion. When the dust clears, the orbit is smaller by orders of magnitude, and the future is set. For black holes, this channel is supported by populations of X-ray binaries and by gravitational wave detections, which confirm that compact remnants do merge. The uncertainties are in mass loss, natal kicks, and spin alignment, which decide whether a binary survives supernovae. Yet the basic outcome is robust, because dissipation inside the envelope is strong and efficiently drains orbital energy. A white hole would need an analogous history, which is already suspicious. A white hole cannot be produced by ordinary collapse in classical general relativity, because collapse generates a future horizon rather than a past one. In the time-reversed Schwarzschild solution, a white hole is not formed by implosion, but appears as a pass-boundary condition. So a common envelope channel can only work if the white hole is primordial, exotic, or a late-time transformation. That means the binary must either form with a white hole already present, or acquire one later, and both options impose severe constraints. The second pathway is dynamical capture in dense environments, where gravity plays billiards with living stars and dead remnants. In globular clusters and nuclear star clusters, repeated encounters swap partners and harden binaries, like a crowded ballroom where the heaviest dancers drift to the center. Three-body interactions can bind two compact objects while ejecting a third, carrying away energy and angular momentum. Gravitational radiation during close hyperbolic passages can also dissipate enough energy to capture, turning a near miss into a bound fate. This pathway is messy but powerful, and it produces eccentric mergers and unusual mass ratios that isolated evolution rarely makes. It also tends to pair the most massive objects, because mass segregation drives them inward over many relaxation times. If a white hole behaves gravitationally like a compact mass, it could be captured into a bound orbit. The problem is that capture implies close passage through a hostile bath of radiation and matter. Dense clusters are not empty arenas. They are filled with starlight, winds, and the debris of stellar evolution, all moving in complicated flows. A compact object that repeatedly swings through that environment is repeatedly perturbed, tidally stressed, and irradiated. For a black hole, these are mostly nuisances that feed accretion and alter spin over long times. For a white hole, if the classic instability arguments apply, these nuisances are existential. The third pathway is not a binary at all, but a birth event near a black hole, where proximity is built in. If a black hole can bounce into a white hole, the white hole could emerge where black holes already live. In that case, the meeting is automatic because the environment is pre-selected by the parent system. The trap is set by the bounce, not by stellar evolution. Before we choose a scenario, we need the orbital clock that governs all of them, because timing is the real antagonist. For two compact objects of masses m1 and m2, gravitational radiation shrinks the orbit on a timescale that depends steeply on separation. The famous Peters and Matthews calculation made that dependence explicit decades before detectors existed, using the quadrupole formula as a practical bridge. Wide binaries can take longer than the age of the universe to merge, even if they are bound forever. The key scaling is brutal, and it sets our suspense, because it turns distance into destiny. The inspiral time goes roughly like a to the fourth power for circular orbits, where A is the semi-major axis. A small change in separation changes the waiting time by orders of magnitude, which is why common envelope shrinkage matters so much. Any white hole that is short-lived will not survive a long inspiral. Eccentricity sharpens the blade, because it concentrates violence into brief repeating moments. In an eccentric orbit, most gravitational wave power is emitted near pericenter, where velocities spike and curvature deepens. That means a system can spend a long time at wide separations, then suddenly rush inward through repeated close passages. If a white hole is fragile, eccentricity could either destroy it quickly or force a rapid encounter before it decays. Mass ratio and spin also decide whether the approach is gentle or violent, and they decide what the waveform can hide. Comparable masses produce strong tidal coupling and loud gravitational waves, because both objects deform the spacetime substantially. Extreme mass ratios produce long, clean-in spirals with weaker back reaction per orbit, like a small body tracing a deep groove. Spins change the last stable orbit and can drive precession and frame dragging, which modulate the signal's phase and amplitude. Astrophysically, black hole spins are not arbitrary, because formation channels leave fingerprints in angular momentum. Stellar mass black holes can have moderate to high spins depending on formation and accretion history, and X-ray reflection spectra hint at rapid rotation in some systems. Dynamical captures tend to randomize spin directions, reducing aligned effective spin on average. Supermassive black holes can spin up through coherent accretion, or spin down through chaotic mergers that cancel angular momentum. For our trap, we ask what spins a white hole would plausibly have, because spin controls how close matter and waves can orbit. If it is primordial, its spin could be small if formed from near-spherical conditions, though early universe perturbations could still seed rotation. If it is a bounce remnant, its spin might reflect the parent black hole's spin, inherited through the interior evolution. If it is a triggered phase during interaction, its effective boundary condition might mimic spin-dependent reflection, changing how perturbations scatter. Now we confront the environment, because white holes are allergic to noise, and the universe is mostly noise. The universe is not empty, even between galaxies, and the background is not merely a metaphor. The cosmic microwave background fills space at about 2.725 Kelvin, with a photon number density near 410 per cubic centimetre. There are also relic neutrinos, starlight backgrounds, cosmic rays, and diffuse gas. For a black hole, this background is mostly irrelevant to stability, because absorption is the default and the mass change is tiny. The horizon absorbs what arrives, and the effect on mass is negligible on human timescales. For a white hole, even tiny and falling radiation can be fatal in many analyses, because the boundary condition is the opposite. The issue is not bulk pressure, but horizon boundary conditions under perturbations, where small disturbances can be amplified. The instability argument is sharpened by gravitational blue shift near horizons, which turns gentle light into harsh stress. Radiation that is low energy at infinity can become high energy in a near-horizon frame, because local observers measure frequencies that climb as they hover closer. In the time-reversed picture, what would be harmless outgoing redshift becomes dangerous incoming blue shift. The white hole becomes a fine-tuned boundary that must hold against an infinite patience of the cosmos. Even if the mean energy density is tiny, the integrated exposure over long times is not, and nature integrates relentlessly. A white hole that must remain pristine for millions of years is asked to defeat the CMB for millions of years, photon by photon. It must also defeat any local photons from stars, dust emission, and accretion flows, even when those sources are distant. The trap is not only gravitational, it is thermodynamic, so we quantify the hostility in practical terms, because numbers remove the illusion of safety. In intergalactic voids, baryon densities can be as low as about 10 to the -7 per cubic centimetre, which sounds like refuge. Yet the CMB is everywhere and isotropic to high precision, and its photons arrive from all directions with relentless regularity. A white hole in a galaxy is worse, because starlight and gas are abundant and anisotropic, producing stronger perturbations. This pushes us toward isolation, and isolation is hard to maintain across cosmic time and cosmic motion. Compact objects drift through halos and clusters where encounters are common, and gravitational potentials shepherd them into busier regions over time. Even a solitary object is bathed in backgrounds it cannot turn off, including gravitational waves from distant mergers that ripple through space-time. If stability requires near-perfect vacuum, the allowed volume of the universe shrinks to a theoretical ideal. The visuals here are almost cruel in their simplicity, because emptiness is never truly empty. A lone compact object hangs in blackness, and the narrator calls it isolated, yet the screen fills with faint arrows of incoming photons. None of them look dramatic, but the physics cares about accumulation and amplification. The universe does not need to be violent to be persistent. Now we build 3 scenarios, each with its own constraints and its own promise, and we keep their jobs distinct. Scenario A is primordial or otherwise exotic formation, where a white hole is a relic. Scenario B is a quantum bounce, where a black hole becomes a white hole after a long delay. Scenario C is triggered emergence, where a white hole-like phase appears during interaction. Scenario A begins in the early universe, where initial conditions can be strange and where our usual formation stories barely apply. A primordial white hole would have to be encoded in the initial data, not produced by collapse, which already separates it from ordinary astrophysics. It would need to avoid immediate poisoning by the hot early plasma and radiation. That already sounds contradictory, because the early universe is the opposite of quiet. In the first minutes after the Big Bang, matter and radiation were tightly coupled, and the mean free paths were short. The sky, from any point, would have been an opaque glare, not the transparent darkness we imagine today. If a white hole's defining feature is resistance to infall, then a dense thermal bath is the worst possible test. The scenario asks for a relic that survives where almost nothing is isolated. To save scenario A, we must assume extreme isolation or protective geometry, and each rescue has a price. Perhaps the white hole is hidden in a region that inflates away from matter, leaving it in a pocket that later becomes an underdense void. Perhaps it is born after reheating in a rare low-density patch, where the local radiation field is suppressed. Perhaps it is microscopic and only later grows through some exotic process. Each rescue adds a cost that must be paid later, because the meeting still has to happen on schedule. If it is isolated, how does it later meet a black hole at all, given that encounter requires proximity and interaction? If it is microscopic, Hawking scale effects and quantum gravity dominate its behaviour, and classical language becomes unreliable. If it is macroscopic, the entropy and stability problems return with more force, because the surface area and exposure are larger. Scenario A also needs a mechanism to place the relic into a bound orbit with a black hole, and gravity alone is stingy. In the field, capture without dissipation is difficult, because two-body gravity conserves energy and angular momentum. In clusters, three-body interactions can bind, but they also expose the object to dense radiation and matter which may be fatal. In galaxies, dynamical friction can bring massive objects together, but it requires interaction with stars and gas, which again threaten stability. So scenario A is a balancing act between isolation and encounter, and the corridor looks narrow from every angle. Too isolated and it never meets anything, remaining a silent relic that never triggers an event. Too embedded and it stops being a white hole, if instability arguments hold, becoming an ordinary black hole or something else. The trap must be set in a narrow corridor of cosmic history, where the environment is quiet enough to preserve it, but structured enough to deliver a partner. Scenario B is the quantum bounce, where a black hole transitions to a white hole, and the singularity is replaced by a quantum bridge. The central idea is that the classical singularity is replaced by a quantum region that connects to an outgoing phase. The black hole interior evolves, then re-emerges as a white hole interior, as though the collapse is reversed after a delay. The outside sees a long delay because of gravitational time dilation. Time dilation is not a detail here, it is the entire gatekeeper, because it separates internal evolution from external witness. Proper time near the core could be short, while external time is enormous, because clocks deep in a gravitational well do not tick like clocks far away. In many models, the bounce time is seen from infinity scale strongly with mass, often as a high power. Depending on assumptions, it can be far longer than the age of the universe for stellar mass holes. This creates a practical obstacle that feels almost like a cosmic joke, because the universe is young compared to many theoretical clocks. The black holes we observe are young on cosmological scales, and the universe itself is about 13.8 billion years old. If the bounce time for a 10 solar mass black hole is vastly longer, then no such bounces have happened yet. The trap cannot be set because the clock has not run. Some models invert that expectation for small holes, making the bounce time shorter for lower masses, which shifts attention to primordial populations. Then primordial black holes could bounce today, producing bursts that might resemble fast transients. Yet small holes also evaporate faster by Hawking radiation, and they are constrained by observations across many wavelengths. The allowed parameter space becomes a thin slice between non-appearance and overproduction. Scenario B also has an orbital problem, because waiting is itself a dynamical challenge in a changing cosmos. If a black hole must wait eons to bounce, it must remain in a stable environment for eons, which is not a trivial requirement. It must avoid merging with other objects, avoid being tidally disrupted by a larger black hole, and avoid accreting enough to change its mass and timescale. The universe is not gentle with long-lived binaries, and galactic centers are especially unforgiving. Still, Scenario B offers a clean way to place a white hole near a black hole, and that simplicity is seductive. Black holes live in binaries and in galactic centres, where other black holes are common and interactions are frequent. If one member bounces, the partner is already present, and the geometry is already strong. The meeting is not arranged, it is inherited, and that inheritance is the scenario's strongest narrative appeal. Scenario C is the most speculative and the most narratively central, because it trades long-term existence for short-term drama. It proposes a triggered emergence, where a white hole-like outburst is initiated by quantum effects during merger or near-horizon interaction. The idea is not a stable white hole travelling through space, enduring millions of years of background radiation. The idea is a phase transition in boundary conditions when curvature, entanglement, or horizon dynamics reach a threshold. In this scenario, the white hole is not a separate object in the sky, and it may not even be a permanent identity. It is a behaviour that appears when black holes interact strongly, like a brief reversal of the usual one-way membrane. The trigger could be the formation of a common horizon, or the approach to it, or the violent nonlinear dynamics of merger. The outburst could be brief, directional, and coupled to gravitational wave emission. Scenario C has a strategic advantage over A and B because it minimises the time spent being fragile. It does not require a white hole to survive for millions of years in a noisy universe, which is where many arguments try to kill it. It only requires a transient violation of the usual absorbing boundary condition, timed to the most extreme moments. That is still extraordinary, but it is less exposed to long-term poisoning. Scenario C also has a strategic weakness, because it risks becoming unfalsifiable if we let it float. If the white hole phase only appears in the most nonlinear regime, we have limited analytic control and fewer clean approximations. Numerical relativity can simulate exotic compact objects with modified boundaries, but quantum triggers are not yet derived from first principles. The scenario can explain anything if we let it, which is why we cannot let it. So we treat scenario C as a hypothesis with a job, and we judge it by whether it earns its complexity. Its job is to tell us what to look for in the data, and what physics must be specified, not merely to sound intriguing. It must produce distinctive signatures that differ from ordinary black hole mergers, and those differences must survive parameter fitting. It must also respect constraints from existing gravitational wave catalogues, which already match general relativity remarkably well. Now we return to the approach itself, because all scenarios converge on orbital dynamics and strong field bookkeeping. Two compact objects nearing each other experience tidal forces that scale steeply with separation, roughly as the inverse cube of distance. For black holes, tides distort horizons and affect energy absorption, a subtle effect that becomes important near merger. For a white hole, tides could distort the horizon boundary condition and change emission patterns, perhaps turning symmetry into beaming. Frame dragging enters when spins are significant, and it makes space-time behave like a moving medium. In Kerr geometry, space-time is twisted, and orbital planes can precess, and that precession modulates the gravitational wave signal. Spin, orbit coupling, changes the inspiral phase and can tilt the orbital angular momentum over time. If one object has an exotic horizon condition, the coupling could imprint subtle differences in waveform phasing, especially in the late inspiral. Gravitational wave-driven inspiral is the main engine that brings compact objects to merger, and it is our best-tested strong field clock. It is well modelled for black holes and neutron stars, and it is the backbone of our control case. For exotic compact objects, the inspiral can deviate through tidal deformability, through absorption differences, and through potential echoes. The deviations are small until late times, which is exactly when the system is hardest to model and easiest to misinterpret. Numerical relativity gives us a partial guide, even when the object is not a standard black hole, because it teaches us what boundary conditions can do. Simulations of horizonless objects, gravastars, boson stars, and reflective boundary conditions show that late-time dynamics can change ring-down structure. Some models produce long-lived oscillations or delayed bursts of radiation because energy can bounce between an effective surface and the potential barrier. The lesson is that boundary conditions matter as much as mass and spin. For a black hole, white hole encounter, the boundary condition is the central unknown, and it is where the trap snaps shut. Does the white hole horizon reflect incoming perturbations, or does it enforce perfect exclusion in a way that remains stable? Does it emit in a controlled way, or in a runaway burst that self-destructs? Does it behave like a time-reversed absorber, or like a metastable surface with leakage that depends on frequency. This uncertainty is not a minor technicality. It is the hinge of the story and the reason we keep returning to definitions. In classical GR, the event horizon is defined globally, so local boundary conditions are not freely chosen like boundary conditions in a laboratory cavity. In effective models, we can impose reflective or partially absorbing conditions near the would-be horizon, treating the object as black hole-like but not identical. Different choices produce different gravitational wave signatures, and those signatures can be compared to data. So we specify what must be decided before we can compute a collision, because computation is where speculation meets constraint. We must decide whether the white hole has an event horizon in the same global sense, or whether it is better described as a temporary apparent horizon. We must decide whether it has a past horizon that remains well defined in a dynamical spacetime with perturbations. We must decide how energy and entropy flow across that boundary, because the second law is not optional. Now we tighten the trap by asking what counts as a successful meeting, and we keep the three collision types separate. For a horizon merger, the white hole must persist through in spiral and not be converted into a black hole by perturbations. It must also allow the spacetime to form a common horizon without contradicting its no-entry rule, which sounds like a direct clash of causal conditions. Even the language becomes strained because common horizon implies a shared trapped region. For a close encounter with mass transfer, the white hole must emit into the black hole's gravitational field, and the geometry decides what is swallowed. Some of that emission will be captured, increasing the black hole's mass and area, and the capture fraction will depend on geometry and relative motion. The encounter could resemble a one-sided accretion event, with the black hole feeding on the white hole's outflow. The question becomes whether the white hole can keep emitting without being choked by back reaction. For a nearby ejection event, the white hole phase can be brief and still matter, because strong gravity edits the message. A burst near a black hole will be lensed, redshifted and partially captured, and the time profile can be stretched by gravitational delays. The black hole's potential will shape the escaping spectrum and arrival times, like a distorted echo in space-time. The gravitational waves from the system could coincide with an electromagnetic or particle burst, creating a multi-messenger clue. Now we examine the orbital mechanics that could place them close at the right time, because proximity is not enough without timing. In binaries, the in-spiral time must be shorter than the white hole's effective lifetime, whether that lifetime is intrinsic or environmentally limited. In clusters, capture must occur without immediate disruption by encounters, which can exchange partners and reset the orbit. In galactic centers, three-body interactions and gas talks can harden binaries, but they also create dense radiation fields that may poison a fragile horizon. The key parameter is eccentricity, because eccentric orbits can produce fast mergers and repeated strong field flashes. Dynamical capture often yields high eccentricity, with repeated close pericenters that act like hammer blows. Each pericenter passage produces a burst of gravitational radiation and strong tidal interaction, and it can also trigger nonlinear effects. If a white hole is fragile, eccentricity could doom it quickly, or it could force the rapid encounter that scenario C prefers. Another key parameter is mass ratio, because it determines whether one object dominates the geometry and the time dilation budget. A small white hole near a large black hole will be strongly time dilated and strongly tidally stressed, making its local physics hard to translate to distant observables. A comparable mass pair will create a highly nonlinear shared spacetime where horizon definitions shift rapidly, and where numerical relativity becomes essential. Each regime changes what meeting even means, because the spacetime itself is being rebuilt. We also consider recoil and kicks, because they can separate systems before they merge or after they do, changing what we can observe. Black hole mergers can impart recoil velocities through asymmetric gravitational wave emission, sometimes hundreds or thousands of kilometers per second. If a white hole phase occurs during merger, the asymmetry could be larger or smaller depending on emission geometry and timing. A kick could eject the remnant from its environment, affecting afterglows, retention in clusters, and the chance of repeat encounters. Now we return to the environmental hostility with a sharper point, because approach can amplify what was previously tolerable. Even if the CMB is cold, it is relentless and isotropic, arriving from every direction like a silent rain. A white hole that forbids infall must maintain that condition against an infinite sky of photons, and the statistics never stop. Gravitational focusing by a nearby black hole can increase the flux near the white hole, bending trajectories and raising local intensity. This is where the trap can fail before it springs, and failure would look deceptively ordinary. The closer the objects get, the more curved space-time becomes, and the more any background field is distorted and concentrated. If the white hole horizon is unstable to perturbations, the inspiral is a perturbation factory, producing tidal distortions and scattering radiation. The system may convert into an ordinary black hole binary before any exotic collision occurs, leaving us with a conventional signal. Yet the same logic can make the encounter spectacular if a white hole phase survives, because the final seconds are a natural amplifier. Near merger, energies are large and timescales are short, and the gravitational wave luminosity briefly rivals that of all stars in the observable universe. A brief outburst could be synchronized with peak gravitational wave power when detectors are most sensitive to deviations. The black hole could act as a lens and a filter, shaping what escapes to infinity and hiding what falls inward. So we ask what a plausible observational signature would require, and we keep the bar high. It would require a deviation from standard inspiral phasing that cannot be absorbed into mass and spin fits, because parameter degeneracies are powerful. It would require altered ring-down damping, possibly with echoes or extra modes that persist beyond expected quasi-normal ringing. It would require a coincident transient that is difficult to explain with ordinary accretion physics, especially if the environment is otherwise clean. We also acknowledge the selection effect that hides rare events, because absence of evidence is not evidence of absence. Gravitational wave detectors are most sensitive to certain masses and distances, and their sensitivity varies with frequency and time. Electromagnetic follow-up is incomplete and biased toward nearby, well-localized events, which many mergers are not. A white hole encounter could be happening and still evade identification if its signature is subtle, short, or outside our follow-up windows. Now we compress the three scenarios into a single decision tree, because clarity is part of the trap. If white holes are long-lived objects, scenario A must solve isolation, and later capture without destroying the defining boundary. If white holes are delayed transformations, scenario B must solve the external waiting time and the survival of the parent black hole for cosmic durations. If white holes are transient phases, scenario C must specify a trigger and a boundary condition that yields testable predictions rather than flexible stories. In all cases, the orbital approach is governed by known relativity until the boundary condition becomes active, and that boundary is the switch. Tidal forces, frame dragging, and gravitational wave emission drive the system toward a shared strong field region where simple intuition fails. Numerical relativity tells us how horizons behave when both partners are absorbers, and it predicts ring down with impressive accuracy. It does not yet tell us what happens when one partner is an emitter by definition, and that gap is where the trap is hidden. So we end with the key unknown that sets up the next chapter, and we state it without decoration. What are the boundary conditions at the white hole horizon in a dynamical, non-empty universe, where perturbations are unavoidable? Does it reflect, absorb, or emit in a controlled way under tidal forcing and irradiation? Without that choice, we cannot compute energy flow, horizon evolution, or observable signals, and we cannot say what collision truly means. Transition. Once they are close, classical general relativity demands we track horizons and energy flow with precision. We enter the moment of impact and ask whether space-time stitches together or tears. They are finally close enough that the word collision stops being metaphor and becomes geometry, because two one-way boundaries approach within the same dynamical space-time. One boundary is defined by swallowing everything that crosses it, while the other is defined by refusing entry even as it emits. On screen, the approach is not a simple impact in empty darkness, because the surrounding universe participates as a distorted optical instrument. Space around them looks thickened and lens-like. Starlight bends into arcs, and the background seems to slide as if the cosmos is being reframed. Distant galaxies smear into crescents, and a few bright stars split into multiple images that drift as the pair tightens. Even the darkness has structure, a kind of sculpted absence that hints at where light paths terminate. In classical general relativity, this is not two hard shells striking like billiard balls, and it is not even two objects in the everyday sense. The relevant entities are horizons and trapped regions, which are global features determined by the spacetime's full evolution. A trapped region is defined by the behavior of light cones, outgoing light rays that should expand instead converge, as if out has been removed from the map. That word global matters, because an event horizon is not a local membrane you can tap with a probe and get an immediate answer. It is a boundary defined by the fate of light rays, and its location depends on what the spacetime will do next. In practice, you can only identify an event horizon after the fact, once you know which null geodesics never reach infinity. Apparent horizons and trapping horizons offer quasi-local substitutes, yet the event horizon remains the strict bookkeeper of escape. So the moment of impact is really a moment of decision about boundary conditions, written into the causal structure rather than onto a surface. Does the white hole remain an emitter? Does it flip into an absorber? Or does the encounter briefly create a bridge? The equations do not choose in a human sense, yet the initial conditions and perturbations funnel evolution into a small set of consistent outcomes. If that sounds abstract, we can translate it into a visual rule that the audience can feel in their bones. Every photon and particle carries a little arrow of causality, and the horizon tells those arrows which futures are allowed. Near the boundaries, the light cones tip so severely that the distinction between toward and away becomes a question of geometry, not preference. We keep one anchor in view as tension rises, because the question is simple even when the math is not. If white holes can exist, what happens when they collide with black holes? And can the universe blink, break, or be reborn? The deeper unease is that both objects are defined by what they forbid, and so their meeting is a meeting of prohibitions. Historically, white holes entered physics as the time-reversed half of a famous solution, discovered in the early decades of relativity. In the maximally extended Schwarzschild geometry, the equations allow a region that only emits, paired with a region that only absorbs. This extension is a mathematical completion of the simplest black hole spacetime, and it reveals extra regions that are not obvious from the exterior metric alone. The white hole appears as a past singularity, the mirror image of the black hole's future singularity, and it makes the diagram look eerily symmetric. That pairing was never a guarantee of reality, because solutions can be mathematically consistent and still physically unreachable. The universe must also provide a way to form the object and to keep it stable. Gravitational collapse naturally produces future horizons, while a past horizon would require the cosmos to arrange matter and radiation in an extraordinarily special way. It is the same reason we do not see broken eggs spontaneously reassemble, even though the microscopic laws allow time reversal. Even so, the idea persists because it touches several deep themes at once: entropy, causality, and the uneasy boundary between classical gravity and quantum fields. It also functions as a stress test for our intuitions, because it asks whether the arrow of time is merely statistical or somehow enforced by geometry. If a white hole were found, it would not just be a new object, it would be a new constraint on what initial conditions the universe permits. Now the two horizons draw near, and the language becomes more precise. One is a future horizon, the black hole's boundary of no return, and the other is a past horizon, the white hole's boundary of no entry. Their one-way character is not a material property, but a statement about which null rays can be extended to infinity. In the simplest picture, they are complementary one-way doors, yet their interaction happens in a space-time that is anything but simple. In a Penrose-style diagram, they look like clean diagonal lines that meet and separate with elegant inevitability. In an astrophysical merger, they are distorted, sheared, and dragged by spin, like ink lines pulled by a current. The horizons bulge and dimple, and their generators twist as frame dragging drags local inertial frames into rotation. The geometry is dynamic, and the boundary is a living structure made of light-like trajectories. Outcome family 1 is the most conservative and, by many arguments, the most likely. The white hole dies first, destabilized by the black hole's environment before any exotic merger can complete. This is not a moral judgment, but a statement about typical perturbations, because the universe is noisy and a white hole demands near-perfect tuning. The closer the black hole comes, the less forgiving the tuning becomes. A white hole is defined by no entry, but the universe does not offer perfect isolation, even in the emptiest intergalactic void. Even in a void, background photons and neutrinos provide persistent perturbations that cannot be turned off. There is also the ever-present gravitational field of the wider cosmos, a slow tidal bias that never truly vanishes, The cosmic microwave background alone fills space with about 400 photons per cubic centimetre, a relic glow from when the universe cooled enough for atoms to form. Their energies are tiny, yet their presence is relentless, and gravity can amplify small inputs. In the white hole's time-reversed bookkeeping, those low-energy photons can become high-energy disturbances in the relevant frame. What looks like a gentle drizzle at infinity can look like a hailstorm near a boundary. Neutrinos add another faint C, slipping through most matter while still carrying stress energy. In general relativity, even a dilute flux contributes to curvature and to what horizons must respond to. Neutrinos also come in flavors and oscillate as they travel, yet for gravity the details do not matter, only the energy momentum tensor does. The horizon responds to the sum, not to the particle identities. Near a horizon, small disturbances can become large in the relevant frame, and this is where the time reversal intuition becomes dangerous. The same gravitational redshift that makes black holes look quiet from far away implies severe blue shift for time-reversed boundary conditions. A white hole, in that sense, is a device that turns the universe's weak background into a strong local perturbation. The instability is not an added feature, it is embedded in the causal geometry. To see why, imagine hovering close to the boundary with rockets firing, holding position against the pull or push of curved space-time. For a black hole, incoming light looks increasingly energetic in that local frame, and for a white hole, the time reversal makes the bookkeeping even harsher. The closer you hover, the more extreme the energy you measure, because your frame is increasingly accelerated relative to distant infinity. The horizon is not a place of infinite energy, but it is a place where frames disagree violently. As the black hole approaches, its tidal field and gravitational focusing concentrate whatever radiation is present. Trajectories that would miss are bent inward, raising flux near the white hole boundary. Even a small angular deflection can matter, because near-horizon geodesics are delicately balanced between escape and capture. The result is a funneling of phase space, not just of light. Visually, the space between them becomes a funnel of light, and the camera lingers on the strange choreography. Faint background rays curve into tight bundles, and the region around the white hole horizon seems to glitter with compressed converging paths. The lensing arcs brighten and thin, like threads being pulled taut, and the empty region between the objects becomes a corridor of distorted starfields. This focusing is not optional because it is built into the Raychaudhuri equation, which governs how congruences of geodesics expand or contract. In plain language, gravity tends to make families of nearby geodesics converge, unless something like negative energy pushes back. The equation also makes clear what pushes back means. Shear, vorticity, and stress energy all contribute, and ordinary matter usually reinforces focusing. So if you want a white hole to remain pristine, you're asking the universe to suppress the very tendencies that curvature encourages. If the white hole is classically unstable, this is the trigger, and the trigger does not need to be dramatic. The emitting horizon cannot maintain its exclusion rule under perturbations, and the geometry reconfigures into a black hole horizon. The phrase "cannot maintain" is shorthand for a deeper statement. The set of null generators that once defined a past horizon is no longer consistent with the evolving spacetime. The boundary that once forbade entry becomes, under perturbation, a boundary that forbids exit. That reconfiguration is not a mechanical flip of a surface, and it is not a hinge turning in space. It is a change in the causal structure. Outgoing null rays that once escaped now find themselves trapped, and the boundary that defines escape shifts accordingly. In numerical terms, the expansion of outgoing null congruences changes sign, and trapped surfaces appear where none existed. Once a trapped surface forms, the global horizon tends to follow, sealing the fate of nearby rays. In many analyses, the instability is immediate because any infalling disturbance accumulates rather than disperses. A white hole must expel matter in a finely tuned way, and even a small mismatch can pile up into a trapped region. The time-reversed nature of the solution means that what would be harmless outgoing radiation in a normal collapse becomes, under perturbation, an incoming contamination that the geometry cannot ignore. The white hole is forced to accept what it was defined to reject, and that contradiction resolves by changing the definition. Then the encounter becomes effectively a black hole merger, and the exotic partner is erased before contact. The story continues with only subtle anomalies in the latent spiral and ring down, like fingerprints smudged before the print is complete. From far away, the gravitational wave chirp can look almost textbook, because the dominant dynamics are still governed by mass and spin. Yet if the boundary conditions were briefly different, the waveform may carry faint scars. Those anomalies would be small and easy to confuse with ordinary parameters, especially when detectors must separate signal from noise. A slight phase shift from altered absorption, a small change in tidal coupling, or a brief non-standard burst of curvature. There could also be a tiny difference in how quickly the system circularizes, because dissipation at the horizons affects the orbit's late-time evolution. Even the excitation of specific quasi-normal modes can be biased by how energy is absorbed versus reflected. The reason they are easy to miss is that gravitational wave templates already juggle many degeneracies, and nature rarely labels its parameters. Mass ratio, spins, orbital eccentricity, and precession can all mimic minor timing changes. A small deviation in the late-in spiral might be absorbed by a slightly different inferred spin, or by a modest eccentricity that is hard to measure. The waveform is a rich code, yet it is also a code with many near synonyms. Even the environment can confuse the story, especially for mergers that occur in messy astrophysical neighborhoods. Gas, magnetic fields, or nearby bodies can add weak perturbations, and a short-lived white hole phase would have to stand out against that clutter. A circumbinary disk can torque the orbit, and plasma can introduce electromagnetic counterparts that tempt us toward the wrong explanation. If the event is at cosmological distance, lensing and detector calibration add further uncertainty. Classical horizon dynamics biases the story toward this outcome, and the bias is not merely aesthetic. Hawking's area theorem says event horizon area should not decrease, assuming reasonable energy conditions and no exotic stress energy. Those assumptions are technical, but the spirit is intuitive. If matter has positive energy, it focuses light rays and makes horizons grow. The theorem is one of the cleanest expressions of irreversibility in classical gravity. The theorem is not merely a slogan, and it is not a hand-waving analogy to thermodynamics. It follows from the focusing of null generators of the horizon, and it treats the horizon like a one-way accounting surface for causal flow. If the null generators are focused and cannot cross, the cross-sectional area they sweep out tends to increase. The proof is delicate, yet the conclusion is robust under the usual conditions of astrophysical matter. Area behaves like entropy in the classical limit, and entropy prefers the absorbing direction, because absorption hides microstates behind a boundary. A final black hole with larger total area is the thermodynamic attractor of the combined system. This is why the white hole feels unnatural. It is a boundary condition that looks like entropy running backward. If you could watch the microscopic degrees of freedom, the white hole would look like an improbable coordination of them all. This is where the mystery becomes almost philosophical, and the narration slows to let the question breathe. A white hole looks like a low entropy boundary condition imposed on a universe that statistically runs the other way. Is that boundary condition forbidden, or merely fantastically unlikely, like a temporary fluctuation in a sea of disorder? If it is merely unlikely, then the universe might still permit it in rare corners, and our job becomes to recognize the trace. In a standard merger, a few percent of the total mass energy is radiated as gravitational waves, and the exact fraction depends on mass ratio and spin alignment. The remnant mass and spin are set by energy loss, angular momentum loss, and horizon growth. That energy loss is not a side effect, it is the mechanism that lets the orbit shrink and the inspiral accelerate. The waves carry away the system's changing quadrupole moment, and they do so with astonishing efficiency near the end. Those waves are not emitted from the horizon itself, and that detail matters for intuition. They are generated by the changing quadrupole of the spacetime curvature, and they carry away information about the orbit's final cycles. The strongest emission comes from the near zone, where curvature is high and the geometry is rapidly changing, yet still outside the horizon. The horizon participates by absorbing some perturbations and by shaping the effective potential that waves must climb. So in outcome 1, the bookkeeping looks familiar, and the narrative returns to a known rhythm. 2 compact masses in spiral, a common horizon forms, gravitational waves carry away energy, and the final Kerr black hole settles by ringdown. The common horizon formation is a topological event in the slicing of spacetime, and it marks the point where separate trapped regions become one. After that, the remnant rings like a struck bell, and the modes damp as energy is radiated and absorbed. On screen, the inspiral is a tightening spiral of warped starfields, with lensing arcs whipping faster as the orbital period collapses. At the moment of common horizon formation, the visuals compress into a single dark core surrounded by a trembling halo. The halo shivers with interference patterns, as if spacetime is trying several shapes before settling on one. A final pulse of distortion ripples outward, and the background snaps into a new, slightly shifted arrangement. Yet the word familiar hides the key question, and we bring it back into focus. If a white hole phase existed briefly, what trace could it leave without violating the area trend that governs classical evolution? The answer, if there is one, likely lives in the details of dissipation and reflection at the boundary. A horizon that is not perfectly absorbing changes how perturbations are stored and released. Even a short-lived modification can alter what the remnant remembers in its ringdown. The best place to look is not the loud chirp, but the fine structure after peak strain, where the signal is quieter but more diagnostic. Boundary conditions at the horizon control damping, and damping controls what the ringdown forgets. The late-time tail is a contest between radiation leaking out and perturbations being swallowed. If the swallowing is imperfect, the contest changes its outcome. Ringdown is often described as a bell-like tone, but the bell is spacetime itself, and the clapper is the violent distortion left by merger. The remnant oscillates in quasi-normal modes whose frequencies depend mostly on mass and spin, and whose decay depends on absorption. These modes are solutions to a wave equation on a curved background with specific boundary conditions, purely outgoing at infinity and purely ingoing at the horizon. Change the boundary and you change the spectrum. Numerical relativity already tests this logic using exotic compact objects, because it is a controlled way to ask what if, without committing to a full theory. Replace perfect absorption with partial reflection, and the waveform can develop late-time echoes, delayed pulses shaped by the potential barrier. The echoes are not magical repeats, they are the natural result of waves bouncing between an inner boundary and the curvature barrier outside. If the boundary is close to where a horizon would be, the delays can be long in coordinate time even when the proper distance is small. That potential barrier is the curved spacetime analogue of a mountain pass, formed by the effective potential in the reggae, Wheeler or Tucholsky equations. Waves scatter off it, and if a reflecting surface sits inside, some energy can bounce back and leak out later. The barrier sits near the photon sphere where light can orbit, and that region acts like a resonant cavity for perturbations. The photon sphere is not a physical ring, yet it is a dynamical feature that shapes wave propagation. A white hole-like boundary is an extreme version of that modification, because it is defined by emission rather than absorption. If it reflects or emits instead of absorbing, the post-merger signal could carry extra structure beyond standard quasi-normal modes. That structure could include phase shifts, altered damping times, or a sequence of faint echoes whose spacing encodes the effective cavity size. The challenge is that the modifications might be frequency-dependent, so the imprint could be uneven across the waveform. The echoes, if they exist, would not be loud repeats of the main event, and we should not imagine a neat series of identical pulses. They would be faint, time-delayed ripples, spaced by a light travel time set by the effective cavity between barrier and boundary. Each echo would be filtered by scattering, so it would arrive stretched and softened, like a sound heard through a long corridor. The later echoes would be weaker because each bounce loses energy to leakage and absorption. But Outcome 1 warns us that the signal may be muted, and the warning is not pessimism but realism. If the white hole collapses early, the system quickly becomes an ordinary absorber, and the window for exotic imprints narrows. The boundary condition would revert to the standard ingoing condition before the remnant has time to trap and re-emit much energy. In that case, the waveform would look almost indistinguishable from a normal merger, except perhaps for a subtle mismatch in the earliest ring-down cycles. That narrowing is crucial because detectors integrate over noise, and the analysis depends on stacking evidence across events. A brief deviation can be swallowed by statistical uncertainty, especially when the event is distant and the signal-to-noise ratio is modest. Calibration errors, non-Gaussian noise transients, and imperfect waveform modeling can all masquerade as small anomalies. This is why the most conservative outcome is also the hardest to falsify. It hides in the same place as ordinary uncertainty. Transition. If the white hole dies first, the universe hides the paradox inside a larger black hole. If it survives longer, the paradox can announce itself violently. Outcome family 2 is the explosive interaction, the horizon fireworks scenario, and it is explosive in a specific, physically constrained sense. Here, the white hole retains an emitting boundary long enough for the black hole to arrive while emission continues. The encounter becomes an interaction between outflow and strong gravitational focusing, with the black hole acting like a lens that can concentrate streams into dense, unstable regions. The violence comes from compression and timing, not from a violation of conservation laws. The key is not that the white hole creates energy from nothing, because general relativity does not grant free lunches. The key is that strong gravity can compress, focus, and blue shift whatever is already being emitted, turning outflow into a weapon. If the white hole is expelling radiation, particles, or magnetized plasma, then the approaching black hole can reshape that outflow into something more intense and more directional. The same emission, redistributed, can look like a burst. To picture it, imagine a lighthouse beam crossing a storm of moving mirrors, where each mirror is a curved space-time region that changes as the orbit evolves. The beam's direction, density, and timing are reshaped, and the reshaping can concentrate power into brief, sharp flashes. Some rays are delayed and then released together, while others are focused into caustics where intensity spikes. The geometry becomes an optical machine that builds transients out of steady flow. As the black hole approaches, its tidal field distorts the outgoing streams, and the distortion is not gentle. Gravitational focusing narrows trajectories, increasing energy density and raising the chance of shocks in surrounding plasma. The tidal field also stretches and squeezes the outflow, creating velocity gradients that are fertile ground for instabilities. If magnetic fields thread the plasma, those gradients can trigger reconnection, turning stored magnetic energy into heat and radiation. In a plasma, shocks are not just sound waves, and the distinction matters because the medium is often collisionless. They are collisionless structures mediated by electromagnetic fields, and they can accelerate particles to extreme energies through repeated scattering. This is the mechanism behind many astrophysical high-energy sources, and it can operate even when particle-particle collisions are rare. The shock front becomes a moving electromagnetic barrier, and particles gain energy by crossing it multiple times. Outflow that would have escaped freely in isolation now climbs through a changing gravitational potential, and the potential is evolving on the same timescale as the flow. Some rays are bent back toward the black hole, some are trapped, and some are delayed and stacked. The stacking is especially important near the photon sphere, where paths can linger and orbit before deciding whether to escape. In that region, a small change in geometry can suddenly redirect a large fraction of the flow. That stacking is a subtle effect with dramatic consequences, because energy density is not about total energy, but about energy per volume and per time. When emission at different times is forced into the same region, energy density rises, and nonlinear interactions become more likely. Pair production can become relevant for high-energy photons, and radiation pressure can reshape the plasma itself. The flow can become optically thick, trapping photons and forcing energy into particles. In the local frame near the interaction region, frequencies can be driven upward, and the narration carefully separates local from distant measurements. Blue shift near horizons is real for hovering observers, even when distant observers later measure a red-shifted remnant. A photon can be born with modest energy, be blue-shifted as it falls into a deeper potential, and then be red-shifted again if it escapes. The path matters, and the observer's frame matters, because energy is not a single global number in curved space-time. This is where misconceptions multiply, so we slow the narrative and do the accounting with discipline. An explosion is limited by available mass energy, not by an imagined infinity at the horizon. The horizon is not a battery, and it does not inject energy into the system. What it does is constrain trajectories, and constraints can concentrate energy in ways that look explosive. The difference between concentration and creation is the difference between physics and fantasy. The maximum budget is set by the masses, their binding energy, and whatever energy is stored in fields and plasma. The horizon does not create energy, it redistributes where energy can go. In a merger, the binding energy released is large, and it is already enough to power the gravitational wave burst we detect. If additional channels convert some of that energy into electromagnetic or particle emission, the burst can be bright, yet it remains finite. In relativity, energy is also frame-dependent, which is why the same photon can look mild far away and fierce nearby. The invariant statement is conservation of stress energy, not a single universal energy number. Local observers measure energy using their four-velocity, and different four-velocities give different measurements. That is not a loophole. It is how curved space-time keeps the books consistent without privileging one observer. Distant observers do not see the same energies that local frames measure, and the difference can be enormous near horizons. Photons and particles that climb out are redshifted, and arrival times are stretched by gravitational time dilation. A short, violent local pulse can be smeared into a longer, softer signal at infinity. Conversely, if focusing creates a narrow escape channel, a modest local flux can appear as a sharp transient to a distant telescope. So the observable burst depends on escape fraction and redshift, not just on local violence. A spectacular local interaction can still look modest at infinity if most energy falls inward. This is the cinematic tension of horizons, and it is also the observational frustration. The most intense physics can happen where signals struggle to escape, so the universe can be both violent and secretive at the same time. Still, outcome 2 can be bright in multiple channels, and we enumerate them without overpromising. If the outflow includes high-energy photons, gamma rays are possible, and if baryons are involved, neutrinos and cosmic rays become plausible. Gamma rays would likely come from internal shocks or magnetic dissipation, where kinetic energy turns into radiation. Neutrinos would trace hadronic interactions and they would escape even when photons are trapped. Cosmic rays would be the most elusive signature, because magnetic fields scramble their directions before they reach us. The surrounding environment matters because it supplies targets for shocks, and it determines whether radiation can be efficiently produced. In a gas-rich region, compressed outflow can drive collisionless shocks that radiate efficiently across the spectrum. The shock heats electrons, amplifies magnetic fields, and produces synchrotron emission that can span radio to X-ray bands. If the region is dusty, optical light can be absorbed and re-emitted in infrared, shifting the apparent color of the transient. In that case, we might see a fast transient, an abrupt flash followed by a fading afterglow as the shock plows into ambient material. The colors would evolve as the emitting particles cool, and the light curve would steepen when the shock decelerates. On screen, the burst could be shown as a sudden bloom around the merging shadows, followed by expanding shells of faint emission. The afterglow would ripple through the surrounding gas, tracing invisible magnetic fields with luminous filaments. In a cleaner environment, the burst may be particle-dominated and harder to see electromagnetically, because there is little matter to shock and little opacity to thermalize. Gravitational waves remain the most reliable messenger, but their deviations may be subtle. The outflow could still carry energy, yet it might escape as a cold wind of particles that barely radiate. In that case, the fireworks exist, but they are mostly silent to our telescopes. The gravitational wave signature in outcome 2 is shaped by asymmetry and timing, and we focus on how emission can couple back to the orbit. A lopsided outflow can impart momentum, changing recoil, and it can perturb the spacetime during peak emission. Recoil, sometimes called a kick, is already predicted for ordinary mergers when gravitational waves carry away net momentum. Extra asymmetry from emission could tilt that balance, changing the remnant's velocity and possibly its final spin direction. If emission is sustained near merger, it can modify the effective mass distribution, even if only transiently. That can shift the phase evolution, alter higher harmonics, and change the ring-down excitation pattern. Higher harmonics are like overtones in the gravitational wave sound, and they become stronger when the system is asymmetric or highly inclined. They can carry clues that the dominant mode hides, because they respond differently to geometry and to perturbations. A small change in the near-zone stress energy can preferentially excite certain modes, yet we keep the same caution as before, because astrophysics is full of engines that flare and mimic each other. Many astrophysical engines produce bursts, and a burst alone is not a fingerprint of a white hole. Black hole accretion can flare, magnetized disks can launch jets, and neutron star mergers can produce gamma-ray bursts. A convincing case would need timing and morphology that resist ordinary explanations, and it would need consistency across multiple messengers. To claim horizon fireworks, we would need coincidences that are hard to fake, and we would need them repeatedly. A burst aligned in time with a compact binary merger, with spectral and temporal features inconsistent with known accretion counterparts. We would also look for unusual polarization signatures, because magnetic geometry imprints polarization in high-energy emission. If the burst lacks the beaming signatures typical of jets, that absence becomes part of the argument. We would also look for absence where we expect presence, because missing pieces can be as diagnostic as present ones. If a burst occurs without the usual afterglow behavior, or without signs of a jet, the mismatch itself becomes a clue. If the host environment looks too clean for an accretion flare, that too becomes evidence. The story would be built from constraints, not from a single dramatic light curve. We also need to avoid the trap of infinite energy storytelling, because it is tempting and because it is wrong. The horizon is not a generator, and general relativity does not allow free energy without a source term in stress energy. The paradox is not about breaking conservation laws. It is about whether an emitting boundary can persist in a space-time that statistically prefers absorption and entropy growth. That returns us to stability and entropy as the hidden levers, and we make the dependence explicit. Outcome 2 requires a metastable white hole boundary that resists poisoning long enough to interact, yet not so long that it becomes implausible. If the boundary is too fragile, it collapses into outcome 1 before fireworks begin. If the boundary is too robust, we must explain why the universe tolerates a low entropy emitter at all. The corridor is narrow, and the merger timescale is unforgiving. So outcome 2 is a narrow corridor between thermodynamic pressure and dynamical timing, and it is the corridor where the encounter could be loud enough to notice. It is also the corridor where the physics is most nonlinear, because outflow, curvature, and plasma can all feed back on each other. The corridor depends on the mass ratio, because an unequal pair produces stronger asymmetries that can enhance focusing. It also depends on the orientation of spins, because spin changes where the outflow is steered. The corridor also depends on spin, because spin drags spacetime around with it, and that dragging is not a minor correction near merger. Frame dragging can twist outgoing streams, changing where energy piles up and where shocks are most likely to form. It can also shift the location of the effective potential barrier, modifying how waves scatter. On screen, the outflow could be shown as spiraling ribbons, twisted into corkscrews as they pass through the rotating geometry. The ribbons compress, brighten, and then fragment into turbulent knots. Transition. If the interaction does not collapse immediately and does not simply explode outward. The geometry has one more option. The encounter can briefly resemble a bridge. Outcome family 3 is the transient wormhole-like phase, a momentary throat or baby universe channel, and it is the outcome that most directly echoes the maximally extended Schwarzschild diagram. In that diagram, black hole and white hole regions are connected by an Einstein-Rosen bridge. The bridge exists as geometry, but it pinches off too quickly to be traversable in classical GR. The pinch-off is not a dramatic snap. It is a causal closure that outruns any signal trying to cross. The historical context matters here, because the Einstein-Rosen bridge was originally proposed as a particle model, an attempt to represent an electron-like object as pure geometry. It later became a symbol of how geometry can mimic connectivity without permitting travel. The idea migrated into popular imagination as a wormhole, yet the original bridge is a very specific, non-traversable structure. Its enduring power comes from the way it teases us with a shortcut while denying it. A merger could, in principle, momentarily create a similar throat-like structure, although the word create must be handled carefully. Two horizons interacting might produce a transient region that looks like a connection between otherwise separated domains. In dynamical spacetimes, horizons can change topology on certain slices, and what looks like two separate trapped regions can become one. The question is whether the intermediate geometry resembles a throat that supports wave trapping in a distinctive way. Visually, this is the strangest branch, and the narration leans into the uncanny without breaking physics. The dark cores approach, and the warped light between them briefly resembles a narrowing tunnel, an hourglass of curvature that forms and then collapses. The starfield appears to pour into the throat and re-emerge in distorted patterns, as if the universe is trying to fold. For a moment, the lensing arcs align into a ring that looks like a mouth, and then the ring shudders and dissolves. We emphasize what classical relativity says before we add speculation, because classical theorems are the baseline. Classical wormholes require exotic stress energy to stay open, and without it, the throat collapses faster than signals can cross. Exotic stress energy is a technical phrase for violating energy conditions, such as the null energy condition. In plain language, it means matter that behaves unlike anything we routinely observe, such as negative energy density in certain frames. Quantum fields can produce such effects locally, but sustaining them macroscopically is another matter. So in classical GR, a bridge phase would be non-traversable and short-lived, and it would not be a stable tunnel for matter. It would not be a safe passage to another universe, and it would not allow a spaceship to outrun causality. Yet even a non-traversable throat can matter observationally, because it changes how perturbations scatter. It can change how waves are trapped and released, and it can change how ring-down energy is partitioned between radiation and absorption. The bridge can function as a temporary resonator even if it never becomes a corridor for travel. A transient throat can act like a temporary cavity, altering the spectrum of quasi-normal modes, and the alteration can be subtle but principled. Even small changes in scattering can leave fingerprints in late-time decay, where the signal is delicate. The late-time tail is sensitive to boundary conditions and to the structure of the effective potential. If a throat changes the potential landscape, it changes which frequencies linger and which die quickly. This is where quantum considerations enter, because classical theorems rely on energy conditions that quantum fields can violate locally. Hawking radiation already shows that horizons are not perfectly classical objects, even if the effect is tiny for large black holes. Hawking's insight was that quantum fields in curved spacetime do not respect the naive vacuum. Particle pairs can be produced near the horizon, and the bookkeeping assigns negative energy to the black hole's interior partner. That negative energy is precisely the kind of ingredient that violates classical energy conditions, though usually in a very small, controlled way. Quantum gravity proposals add a sharper possibility, and we present it as a question rather than a conclusion. Black-to-white transition could release stored information and energy, reframing the information paradox as delayed emission rather than destruction. The information paradox itself is a clash of principles, unitarity in quantum mechanics versus apparent loss behind horizons in classical gravity. White hole-like emission is one proposed escape route, though not a settled one. Some models imagine a bounce that turns the interior into an expanding region, yet the external signature depends on how and when that bounce couples to the outside. But timescales decide whether this matters for a collision, and timescales are merciless. Hawking evaporation is negligible for astrophysical black holes, and any quantum bounce must compete with merger times and accretion. For a stellar mass black hole, evaporation time dwarfs the age of the universe, so ordinary Hawking leakage is irrelevant during a seconds-long merger. Unless new physics accelerates it dramatically, the quantum effects remain whispers compared to the classical roar. Back reaction is the other decisive term, and we explain it in the simplest, honest way. If quantum emission is strong enough to modify the horizon, it must also modify the geometry that defines the horizon, and that feedback can quench or amplify effects. Back reaction is the self-consistency requirement, and it is where many hand-waving stories fail. You cannot add a quantum flux as an afterthought, because its stress energy curves space-time, and the changed space-time changes the flux. The system must be solved together, or the narrative is incomplete, so outcome 3 is not a free fantasy of portals, even if the visuals invite that temptation. It is a question about whether quantum stress energy can briefly support a throat, and whether the support survives in a violent dynamical space-time. If it does, the encounter could resemble a channel into a baby universe, or into another region of space-time. From our side, that might look like missing energy, altered ring-down, or unusual correlations in the waveform. The correlations could be subtle, like phase relationships between modes that standard mergers do not typically produce. Missing energy here means energy that fails to appear in gravitational waves or light, beyond what standard models predict, and it would be inferred rather than directly seen. It would be inferred indirectly through careful comparison of inspiral mass estimates and remnant properties. If the inspiral indicates a certain total mass, but the ring-down suggests a remnant that is too light given the observed radiation, something has carried energy away. That something could still be mundane, like modelling error, so the inference would require high precision and multiple events. Yet we do not promise a clean signature, because the channel could be causally sealed, and nature is under no obligation to be legible. A baby universe branch could carry away information without returning a readable signal to our detectors. That possibility forces a sobering question, and we let it hang. If nature can hide information in disconnected branches, What does it mean to say we have fully measured an event? Even our best detectors would then be reading only the accessible boundary of a larger story. This is where language about space-time tearing must be corrected, because the metaphor is common and misleading. General relativity predicts extreme curvature and geodesic deviation, not literal ripping like fabric under tension. Tidal forces are encoded in curvature, and they act by separating neighbouring geodesics. Near merger, those tides can disrupt matter and plasma, but the manifold remains mathematically intact. The fabric analogy is useful for intuition, yet it breaks when we imagine the fabric snapping. On screen, the tearing is better shown as stretching, and the visuals can teach the correct idea without a lecture. A cloud of test particles elongates into filaments, and the spacing between nearby trajectories grows as curvature gradients intensify. Some filaments twist due to frame dragging, and others compress into sheets as different tidal axes compete. The camera can track a ring of particles that becomes an ellipse, then a line, then a spray. Geodesic deviation made visible. If there is a breakdown, it means the classical description fails, and failure has a specific meaning in physics. A quantum gravity regime would be signalled by the need for new degrees of freedom, not by a visible crack in space. So the real fear is not tearing, it is loss of predictability from incomplete theory. A collision that drives curvature toward the Planck scale would push us beyond tested equations. The Planck scale is not just a number, it is a warning label. It marks where quantum fluctuations of geometry are expected to matter, and where smooth space-time may no longer be the right language. Numerical relativity marks the frontier where we can still compute, and it is one of the triumphs of modern gravitational physics. It handles black hole mergers with high precision, and it can test exotic boundary conditions as effective models. Those computations evolve Einstein's equations on supercomputers, tracking how horizons form and settle. They also let us insert what-if boundaries, reflective surfaces, modified absorption, or delayed emission, so we can see how the waveform responds. The simulations are not just animations, they are solutions to a set of coupled nonlinear equations. In those effective models, reflective surfaces and modified horizons can produce gravitational wave echoes, and echoes have become a recurring motif in the search for beyond-horizon physics. Echoes are not proof of white holes, but they are a template for how boundary conditions imprint signals. A white hole boundary, if it persists, is a radical boundary condition. It could reflect incoming perturbations, emit outgoing ones, or do both in frequency-dependent ways that change late-time structure. Frequency dependence matters because real systems are not perfect mirrors, and because quantum-inspired reflectivity often depends on wavelength. So we end this chapter with a three-branch map, not a single answer, and we treat the map as a guide for what to look for. One branch collapses to a larger black hole. One branch produces finite but violent fireworks. One branch hints at a transient bridge. Each branch is controlled by the same hidden variables: stability under perturbations, entropy flow at horizons, and quantum back reaction in the regime where classical theorems may fail. The map is not a prediction. It is a set of conditional statements about how geometry can respond. The central question remains our compass, now sharpened by dynamics and by the reality of measurement. If white holes can exist, does their meeting with black holes erase them, announce them, or redirect them into new space-time? We can also ask a quieter question, because it is the kind the universe often answers. If the exotic option exists only briefly, would we recognize it, or would we file it away as noise? The history of astronomy is full of signals that were first dismissed as artifacts, only to become discoveries later. Transition. If any of these outcomes happen, the universe should leave traces. We pivot from theory to detection and ask what astronomers would actually see. If any of these outcomes happen, the universe should leave traces, yet traces are not confessions. A black hole and a white hole would not label themselves in the data, and nature rarely provides a clean caption. We would have to infer an impossible boundary condition from imperfect messengers, while admitting that every measurement is filtered through instruments, models, and noise. In practice, that means we do not see a horizon the way we see a planet. We see a pattern of energy and phase, and then we ask what space-time geometry could have produced it. The deeper question is almost philosophical. When the only evidence is radiation, how do we tell absorption from reflection, or silence from a carefully timed reply? We start with the cleanest channel, because gravity ignores dust and distance. Gravitational waves carry the orbital story with minimal astrophysical interpretation, since they are generated by bulk motion of mass energy, rather than by hot plasma. They also carry the strongest test of whether horizons absorb exactly as Kerr predicts, because the waveform is shaped by how the compact objects respond to tides and perturbations. Visually, imagine the detectors as 3 distant seismographs, listening to space-time itself. The signal arrives as a rising tone, then a sharp click, then a fading hum, an audio signature that can be translated into geometry. The remarkable fact is that general relativity predicts that signature with high precision, and it predicts it using only a few macroscopic parameters. In ordinary mergers, the waveform follows a disciplined arc. In spiral is a chirp whose phase is set by masses and spins, and the phase evolution can be computed in a post-Newtonian expansion that becomes more relativistic each orbit. Merger is a brief nonlinear burst, where the 2 horizons and their surrounding curved space-time become a single distorted remnant. Ringdown is a sum of quasi-normal modes that decay with Kerr-like damping, like a struck bell whose tone is fixed by its shape. That bell analogy is more than poetic, because quasi-normal modes are eigenfrequencies of the space-time itself. The real part of each frequency sets the oscillation rate, while the imaginary part sets the damping time. In classical GR, those numbers depend only on the remnant's mass and spin, which is a concrete expression of the no-hair idea. A white hole involvement would first appear as a deviation from that arc. The inspiral could show subtle phase shifts from altered dissipation near the compact object, because a true horizon absorbs perturbations in a specific way. The merger could include extra bursts if emission or reflection injects stress energy near peak strain, briefly reshaping the curvature that launches the gravitational wave. Even small changes matter, because matched filtering is exquisitely sensitive to phase. Over dozens to hundreds of cycles, a tiny systematic phase drift can accumulate into a measurable mismatch. That is why the inspiral, which looks gentle on a plot, often carries the most precise information about the system. The most discussed signature is late-time echoes, yet echoes are not a single prediction. Echoes require an effective cavity between an inner boundary and the photon sphere potential barrier, where null geodesics can orbit and where perturbations can be temporarily trapped. If the white hole boundary reflects or re-emits, some perturbations can bounce and leak out later, producing a train of repeating weakening pulses. In visual terms, the photon sphere is like a steep ridge around the remnant, a region where light and gravitational perturbations can circle before escaping. A horizon behaves like a one-way sink beneath that ridge, while a reflective boundary behaves like a wall. The difference is not a dramatic new peak at first glance, but a faint afterimage, returning after the main event has already faded. Echo timing would encode an effective light travel delay near the would-be horizon. The delay can be long in coordinate time even for tiny proper distances, because gravitational redshift stretches clocks near the boundary. A surface located only a microscopic distance outside the classical horizon can still generate echo delays of milliseconds for stellar mass remnants, and much longer for supermassive ones. Echo amplitude would likely fall quickly, because each bounce loses energy to leakage and absorption. The photon sphere barrier is not a perfect mirror, and the inner boundary may not be either. In many models, the first echo is the strongest, and later echoes become progressively harder to distinguish from the detector's own restless background. But detector reality is the antagonist, and it is not subtle. LIGO, Virgo, and Kagra operate in a band where noise is coloured and non-stationary, shaped by seismic motion at low frequencies and quantum shot noise at high frequencies. The noise is not simply random white fuzz, but a living spectrum with lines, drifts, and occasional bursts. Glitches can mimic short post-merger features, and they often occur without warning. Some are instrumental, like scattered light or control system transients, while others are environmental, like distant storms or local human activity. Weak echoes live exactly where calibration and waveform systematics are most dangerous, because the post-merger signal is short and the detectors are least forgiving there, so the claim standard has to be brutal. An echo search must control look-elsewhere effects across many templates and time windows, because if you try enough patterns you will eventually find one. It must show consistency across detectors and observing runs, since a real astrophysical signal should appear with the right time delays between sites. It must survive reanalysis with different noise models, not just one pipeline, because robustness is the only antidote to wishful pattern matching. Even without echoes, ringdown itself can be a fingerprint. Kerr predicts a specific spectrum of quasi-normal modes set only by remnant mass and spin, and the dominant mode is expected to carry most of the ringdown energy. A white hole-like boundary could shift mode frequencies, change damping times, or excite extra long-lived components, especially if the boundary partially reflects perturbations back into the exterior. One subtle possibility is mode mixing, where the observed ringdown is not a clean single tone but a superposition whose relative amplitudes differ from Kerr expectations. Another is a late-time tail that decays more slowly than predicted, as if energy is being stored near the remnant and released in stages. These are small effects, yet they are conceptually sharp, because they point directly to boundary conditions. We would look for non-Kerr ringdown modes and for inconsistent mode relationships. We would also look for energy stored and released late, which would change the ringdown tail and possibly alter the phase of the late waveform. Yet low signal to noise makes ringdown test hard, because few events are loud enough, and because the ringdown lasts only a handful of cycles above the noise. Historically, this is why the first gravitational wave detections were both triumphant and incomplete. They confirmed the broad GR narrative, but they did not immediately provide the fine spectroscopy that theorists dream about. Black hole spectroscopy, in the strict sense, requires multiple resolved modes, and that is still a frontier rather than a routine measurement. Parameter estimation is where the mystery becomes quantitative. LIGO and partners infer chirp mass, mass ratio, effective spin, precession, distance, and inclination, using Bayesian inference that compares data to families of waveform models. They also infer a remnant mass and spin consistent with energy, and angular momentum radiated away, closing a kind of accounting loop. That bookkeeping is not cosmetic because the in-spiral tells us how much binding energy is lost, and the merger tells us how much is radiated as gravitational waves. In GR, the numbers have to add up within uncertainties, and the remnant's properties must be compatible with the waveform's final frequency and damping. When the accounting fails, it may be a hint, or it may be a warning that our model assumptions were too narrow. A white hole involvement could show up as an anomaly in that bookkeeping. The in-spiral might imply one total mass, while the ringdown implies a remnant inconsistent with expected radiated energy, even after accounting for measurement uncertainty. The mismatch could look like missing energy, or like extra energy injected late, and either way it would force us to ask where that energy went. We would also watch for unexpected tidal deformability. Black holes have effectively zero tidal of numbers in classical GR, meaning they do not develop a static quadrupole response to an external tidal field. Horizonless or non-standard boundaries can produce non-zero tidal responses, which imprint phase corrections in late in-spiral, especially when the objects are close enough that tides matter. This is a delicate measurement because tidal effects are small for compact objects, and they compete with spin effects and with waveform systematics. Still, the conceptual clarity is powerful. A non-zero love number is a direct statement that the object's exterior field responds like matter, not like a perfect horizon. If we ever measured such a response in a system otherwise consistent with black holes, it would be a profound crack in the classical picture. Yet degeneracy is the constant threat. Spin-induced precession can mimic some phase shifts, because precession modulates the waveform's amplitude and phase in a way that can be confused with other corrections. Residual eccentricity can mimic others, because eccentric orbits add harmonics and change the timing of periastron passages. Higher harmonics and inclination effects can hide in noise, then reappear as apparent anomalies when models are incomplete. Even the detector's calibration can play a role, because small frequency-dependent errors can tilt the inferred phase evolution. That is why collaborations devote enormous effort to calibration uncertainty, and why independent waveform families are used as a cross-check. The goal is not to eliminate uncertainty, which is impossible, but to keep it from masquerading as exotic physics. So we need a disciplined comparison set. We would test the same data against standard black hole templates and against modified boundary templates while being explicit about priors and model complexity. We would demand that the exotic model improves evidence without overfitting, because a flexible model can always chase noise. We would also demand that inferred parameters remain physically consistent across waveform segments, since a real system cannot change its mass or spin mid-signal. The second messenger is light, and light is both helpful and treacherous. Typical black hole mergers are electromagnetically dark because there is little matter to radiate and because any tenuous gas is often too diffuse to respond on merger timescales. If we see light, we must ask whether it is environment, coincidence, or new physics, and we must ask that question with humility. The visual temptation is strong because photons feel familiar. A gamma ray flash on a sky map looks like an event, and a fading optical source looks like a story. Yet the sky is always doing something, and the universe has a talent for producing fireworks that have nothing to do with our gravitational wave trigger. If matter is present near the collision, the encounter could produce a short gamma ray burst. It could also produce an X-ray afterglow as shocks decelerate in ambient gas, converting kinetic energy into radiation. Radio transients could follow as the blast wave expands and synchrotron emission peaks later, often on timescales of days to months. The physics of these afterglows is well studied in other contexts, and it gives us useful handles. Synchrotron spectra have characteristic breaks, and their temporal rise and decay encode the outflow's energy, opening angle, and the density of the surrounding medium. If a black hole merger produced an afterglow, we could compare its evolution to known jet models and ask what engine could plausibly power it. A white hole-like outflow changes expectations because it supplies energy and possibly baryons. A nearby ejection event could seed a relativistic outflow without a neutron star, and it could do so on a timescale that is naturally tied to the merger. A mass transfer flyby could feed a black hole and power a jet-like transient, even if the system began as a nominally clean binary. In imagery, this would look like a sudden needle of light, punching outward from an otherwise dark region. A jet would carve a narrow cone, while a more isotropic outflow would inflate a broader, slower shock. The detailed light curve would become a forensic record of geometry, and geometry is where exotic boundary conditions might leave their most distinctive fingerprints. But the sky is full of fast transients, and many are unrelated. Magnetar flares can produce short gamma-ray flashes and radio bursts, and they can do so from galaxies that happen to sit inside a large localization region. Accretion disks around black holes can flare and launch jets, especially in active galactic nuclei where variability is the norm. Even tidal disruption events can produce confusing high-energy variability, with timescales and spectra that overlap our expectations. So association is everything, and association is hard. Gravitational wave localization is often hundreds of square degrees, a patchwork of probability across the sky rather than a single point. A short gamma-ray burst is strongly beamed, so most events point away from us, and the ones we see are a biased subset. A real counterpart could exist and still be invisible, either because it is off-axis or because dust and distance erase it. When we do see a candidate counterpart, timing becomes the first filter. A prompt gamma-ray flash within seconds of merger is suggestive, because it narrows the space of coincidences dramatically. An afterglow that rises and fades with a shock-like profile strengthens the case, especially if its spectrum matches synchrotron expectations. A host galaxy environment that is unusually clean for accretion flares adds weight, because it reduces the list of mundane engines. Yet even perfect timing does not prove a white hole. Neutron star mergers produce similar gamma-ray bursts and afterglows, and they are already a confirmed multi-messenger source. Some black hole mergers could occur in gas-rich disks around active galactic nuclei, producing light without exotic horizons, and those environments can also produce neutrinos and cosmic rays. The same photons can be the signature of radically different engines, so we would look for mismatches with known engines. A burst without kilonova signatures would argue against neutron star ejecta, because kilonova light is powered by radioactive decay of heavy elements synthesized in neutron-rich outflows. A burst with unusual spectral evolution or polarization could hint at non-standard outflow geometry, because polarization carries information about magnetic fields and asymmetry. A counterpart in an environment lacking dense gas would challenge disk-driven explanations, because disks need fuel and dense surroundings to shine. Neutrinos offer a different kind of honesty, because they ignore dust and escape dense regions. High-energy neutrinos require hadronic acceleration, which usually means shocks with baryons, where protons can be accelerated and then interact to produce pions. Those pions decay into neutrinos, carrying away energy that photons might not reveal. An ice cube-like detector would look for a temporal and directional coincidence, using the fact that neutrino arrival times can be compared to the gravitational wave trigger. A single neutrino is rarely decisive, because backgrounds exist and because angular resolution is limited. A cluster of neutrinos around the merger time would be far more persuasive, especially if energy and direction match expectations from a transient accelerator. But a clean vacuum merger should be neutrino silent. If the system is two compact horizons with no matter, there are no hadrons to accelerate, and there are no dense photon fields for hadronic interactions. Gravitational waves carry energy, yet they do not produce neutrinos efficiently in empty space, because there is no medium to convert curvature into particle cascades. So neutrinos become a discriminator between branches of our earlier outcomes. Outcome 1, collapse to an ordinary black hole merger, likely stays dark in neutrinos, and that darkness is itself informative. Outcome 2, horizon fireworks with baryons, could produce neutrinos and gamma rays, because baryons provide the raw material for shocks. Outcome 3, a transient bridge, might produce missing energy hints without strong neutrinos, which would be a different kind of puzzle. Cosmic rays are the most ambiguous messenger, because magnetic fields erase pointing. A collision could accelerate ultra-high energy particles in shocks or reconnection, and the energy budget of compact mergers is, in principle, enormous. Yet by the time they reach Earth, their paths are scrambled by galactic and intergalactic fields, turning a directional clue into a statistical smear. So cosmic rays would be population evidence, not single event proof. We would look for statistical correlations between merger directions and cosmic ray anisotropies, and we would do it over many years of data. We would also look for unusual composition or energy spectra that suggest a new acceleration environment, because composition can hint at where and how particles were launched. Now we confront the hardest truth about multi-messenger claims. Many signals mimic other events, and our detectors are not omniscient, especially when localization is broad and signals are weak. A white hole could hide inside ordinary astrophysical clutter, or it could imitate a known transient class too well, leaving us with a perfect counterfeit. False positives are not just possible, they are expected. Echo-like features can be produced by noise transients and by imperfect subtraction of the main signal, especially when waveform models do not capture all relevant physics. Short gamma-ray bursts can be unrelated background events in the same sky region, because the universe produces them frequently. Neutrino coincidences can occur by chance when localization is broad, and chance is patient when we search long enough. So the statistical standard must be explicit and conservative. We would demand Bayesian evidence ratios that remain strong under prior changes, because fragile significance is often a sign of overinterpretation. We would demand that the anomaly persists across waveform families and calibration versions, because real signals survive reasonable modeling choices. We would demand that independent teams reproduce the result with different methods, because scientific credibility is built on redundancy. We also need a physical standard, not only a statistical one. A claimed white hole signature must fit into a self-consistent energy budget, where radiated gravitational wave energy, any electromagnetic output, and any kinetic outflow can be reconciled. It must not require unphysical negative masses or superluminal emission, even as we explore exotic boundary conditions. It must respect what general relativity and quantum field theory already constrain, because radical claims must still obey the parts of physics that have already passed ruthless tests. This is where the earlier boundary condition question returns as a practical problem. Does the white hole horizon reflect, absorb, or emit under perturbations, and does it do so linearly or with thresholds? Each choice predicts different gravitational wave tails and different energy partition into other messengers. Without a boundary model, we can always retrofit an explanation after the fact, which is the opposite of prediction. So detection becomes a two-step logic. First, we find anomalies that resist standard explanations, and we quantify how resistant they are under skeptical reanalysis. Then we test whether a white hole-like boundary condition predicts those anomalies without fine-tuning, using a model that is specific enough to fail. The second step is harder, because it requires a theory that is not just imaginative, but disciplined. Imaging enters as a temptation, because the Event Horizon Telescope has made shadows feel tangible. Could we ever image a white hole-like emission region, or see a post-merger remnant shadow that looks wrong? The appeal is obvious. A picture feels like proof, even when it is really an inference from sparse data. For stellar mass mergers, the answer is effectively no, because angular sizes are microscopic. Even in our galaxy, a 10 solar mass horizon is far too small, subtending an angle far below any feasible baseline. The timescales are also too fast, because merger dynamics unfold in milliseconds to seconds, while imaging campaigns integrate over much longer times. For supermassive systems, imaging is less hopeless, yet still brutal. EHT resolves horizon-scale structure for nearby giants like M87 and SGRA, where the gravitational radius spans microarc seconds on the sky. A supermassive merger would evolve over hours to days near the end, but the event would likely be far away and heavily obscured. Even if it were nearby, the accretion flow could hide subtle boundary effects behind turbulent emission. A white hole-like emission region could, in principle, look like excess brightness near the shadow edge. It could also look like time-variable structure inconsistent with standard accretion models, perhaps a flare that appears too centrally concentrated or too abruptly timed. Yet accretion turbulence already produces variability, and interpreting deviations would be contentious, because plasma physics is messy and often under-constrained. Future imaging arrays could improve resolution and cadence. Space-based very long baseline interferometry could extend baselines beyond Earth's diameter, sharpening the effective beam and reducing ambiguity in reconstructed images. Multi-frequency imaging could separate scattering effects from intrinsic structure, which matters especially for sources like SGRA. Even then, we would likely infer boundary conditions indirectly, not photograph them directly, because the shadow is a lensing feature rather than a literal silhouette. The most promising gravitational wave frontier is not better pictures, but better spectra. Higher signal-to-noise lets us resolve subtle phase corrections and multiple ring-down modes, turning a single detection into a richer test of strong-field gravity. It also lets us test consistency between in-spiral and ring-down with less degeneracy, because parameters become more tightly constrained. That is why future observatories matter to this story. Einstein Telescope and Cosmic Explorer would detect many more events with higher signal-to-noise, shifting the field from rare discoveries to precision surveys. They would extend sensitivity to lower frequencies, capturing more in-spiral cycles and tightening parameter estimation. More cycles mean more opportunities for tiny deviations to accumulate into measurable phase differences. With higher signal-to-noise, we can test for small tidal deformability and small absorption differences, which are otherwise buried under uncertainty. We can also search for echoes with less ambiguity, because the post-merger signal would sit higher above noise, and because multiple detectors would provide stronger coherence checks. A single loud event could be suggestive, yet a population would be decisive, because patterns across many masses and spins are harder to fake. LISA changes the scale of the question, because it listens to supermassive binaries. It will track in spirals for months to years, measuring phase evolution with exquisite precision, and it will do so in a frequency band where the in-spiral is slow and information-rich. If a white hole-like boundary modifies dissipation, LISA could see the accumulated phase drift, because tiny per-orbit effects can integrate into large measurable offsets. LISA also enables early warning for multi-messenger campaigns. It can predict merger times and sky regions in advance for some systems, shrinking uncertainty as the in-spiral progresses. That allows coordinated electromagnetic and neutrino monitoring, reducing the chance that a counterpart is missed. It also changes the psychology of the search, because we can watch a region of sky with anticipation, rather than scramble after the fact. Next-generation gamma-ray facilities would sharpen the electromagnetic side. Wider fields of view increase the chance of catching prompt flashes, which are otherwise easy to miss. Better localization reduces false associations, because it shrinks the overlap between unrelated transients and the gravitational wave map. Polarimetry can test jet structure and magnetic geometry, which could distinguish outflow scenarios that otherwise look similar in brightness alone. Next-generation neutrino detectors would sharpen the particle side. Larger volumes increase detection rates for transient sources, and improved reconstruction can tighten angular uncertainty. Better angular resolution reduces coincidence backgrounds, which is crucial when gravitational wave localizations are broad. If white hole involvement produces baryon-loaded shocks, neutrino statistics could become a real discriminator, rather than a tantalizing anecdote. Yet even with better instruments, ambiguity does not vanish, it just moves. Exotic compact objects can mimic some signatures without being white holes, and the taxonomy of alternatives is already crowded. Boson stars can alter tidal responses and ring down, because their matter fields support different multipole structures. Graver stars and other horizonless models can produce echoes because a surface can reflect perturbations even if it is not a white hole boundary. Even ordinary astrophysics can surprise us. Magnetar engines can produce repeated bursts and complex afterglows that complicate association, especially when localization overlaps star-forming galaxies. Accretion instabilities can create quasi-periodic variability that resembles echoes in some analyses, particularly when signal processing is aggressive. Plasma lensing can distort radio transients in ways that look exotic, bending time and frequency structure into misleading shapes. So the decisive test may require a population, not a single miracle event. If many mergers show the same post-merger echo-spacing scaling with mass, that pattern becomes hard to dismiss because it ties directly to the remnant's characteristic length scale. If many events show consistent in spiral ring-down energy mismatches, the bookkeeping becomes a clue rather than a fluke. The universe is noisy, but it is also repetitive, and repetition is where inference becomes strong. Population tests also let us control selection effects. We can compare events in gas-rich environments to events in clean environments, using galaxy catalogues and electromagnetic surveys as context. We can test whether anomalies correlate with mass, spin, or redshift, which would hint at formation channels and evolutionary history. We can ask whether the anomaly rate is consistent with any plausible formation channel, or whether it demands something rarer and stranger. Now we widen the lens to cosmological side effects, because the biggest claims live there. Could a black hole, white hole collision see primordial perturbations or local expansion, leaving a scar on the surrounding universe? Could it trigger a baby universe, a new region of space-time budding off from our own? Any new universe branch is likely causally disconnected from our side. If a throat pinches off, the new region becomes a separate space-time domain, and causal signals cannot traverse a sealed horizon back to us. From our perspective, it would not send messages back through a closed boundary, no matter how dramatic the interior becomes. Observable effects would be indirect, like missing energy or altered ringdown, which are subtle and easy to misattribute. Seeding perturbations is also constrained by scale. A single event in the late universe cannot rewrite the cosmic microwave background, because the CMB encodes conditions from a much earlier epoch and over vast volumes. It could, at most, create local gravitational potential perturbations or contribute to stochastic gravitational wave backgrounds. Those would be subtle and easily confused with other structure formation processes, especially when cosmic variance limits what we can know. Local expansion effects would require exotic stress energy or effective negative pressure. Classical general relativity does not give that for free in compact mergers, where energy is concentrated and gravity is overwhelmingly attractive. Quantum effects could violate energy conditions locally, yet sustaining a macroscopic expansion bubble is another demand entirely. The question becomes not whether violations can occur, but whether they can persist and grow without collapsing under their own constraints. So we treat cosmological claims as the far edge of inference, not the first conclusion. The data we can realistically access are gravitational waves, photons, neutrinos, and particles, each one carrying a different slice of the event. Each messenger can hint at boundary conditions, yet none can certify a baby universe directly, because certification would require communication across a boundary that may be defined by no communication. This chapter's tension is that detection is possible in principle, yet proof is hard in practice. The universe offers signals that are partial and noisy, and it offers them on timescales that are often inconvenient for our instruments. Our instruments offer sensitivity that is impressive, yet limited, and their limitations can masquerade as mysteries. The impossible, if it happens, will try to look ordinary, because ordinary is where our priors live. Transition. After surveying signals, we return to the biggest claim, because it is the one that reshapes everything. Could a collision create a new universe, or does physics forbid that story, no matter how imaginative we become? We end with the investigative posture, not a verdict. A white hole would be an argument about causality made visible, a reversal of the usual one-way logic of horizons. If the data ever force us there, it will be because every ordinary explanation failed first, and failed under repeated skeptical pressure. The final chapter weighs that possibility against what the laws allow, and against what the universe has already told us, in signals that are faint but stubborn. We return to the hook in its strictest form, where metaphors stop helping and equations take over. The swallow meets the fountain, and the universe must choose one causal story, one direction for time, one accounting of energy, one consistent horizon. The central question was never just spectacle, or a cartoon of opposites colliding in space. If white holes can exist, what happens at collision, and what could we ever verify with instruments that only see the outside? Start with the conservative verdict, because physics already has a strong bias toward ordinary endings. In known general relativity with ordinary matter, the most likely end state is collapse into a larger black hole, because trapped surfaces are easy to form and hard to erase. White holes are time-reversed solutions, not naturally formed objects, and they demand impossible initial conditions. In the classic maximally extended Schwarzschild geometry, a white hole region exists on paper, yet it is not produced by gravitational collapse in our universe. Any realistic environment perturbs them, and perturbations are amplified near horizons by extreme blue shift. What looks like a gentle drizzle of radiation far away becomes, near the would-be white hole horizon, a violent influx of energy density, enough to destabilize the entire boundary condition. That instability is not a detail, it is the main plot, because horizons are amplifiers of small mistakes. The cosmic microwave background, neutrinos, dust and tidal focusing provide a steady contamination that a white hole cannot ignore, even in the emptiest intergalactic void. Picture the scene in visuals: a dark, compact object framed by a thin, bright lensing ring, while faint background photons stream inward. In a white hole interpretation, those photons are not harmless, because their frequencies climb as they approach the horizon, and their stress energy back-reacts on the geometry. There is also a dynamical reason the conservative outcome wins beyond mere pessimism. In collapse, the formation of a trapped surface is a local condition, and once it forms, the causal structure funnels future-directed paths inward, making reversal extraordinarily difficult. Entropy arguments push the same direction, and they are older than most of our detectors. Since Bekenstein and Hawking, black hole area behaves like entropy, and the generalized second law prefers horizons that absorb rather than emit, because coarse-grained disorder tends to increase. In plain terms, a white hole would be an entropy miracle performed continuously, not once. It would have to eject highly organized energy while refusing to swallow the messy environment, and that is exactly the kind of fine-tuning thermodynamics punishes. So the conservative conclusion is not a guess about personalities of objects or a preference for darkness. It is the attractor of typical initial conditions plus area increase, plus the fact that event horizons quarantine information from distant observers. In that conservative branch, the collision becomes a black hole merger in practice, even if you began with something exotic. Two compact masses in spiral, a common trapped region forms, and ring-down settles to an ordinary Kerr remnant, with mass and spin fixed by energy and angular momentum balance. We can even narrate the phases the detectors would hear, because they are now familiar. The chirp rises as the orbit shrinks. The merger produces a short burst of nonlinear gravity, and the ring-down is a superposition of quasi-normal modes, spacetime's own damped tones. A catastrophic universe-wide rupture is unlikely in this framework, and not because physicists lack imagination. General relativity predicts localized extreme curvature and new horizons, not a global tear that propagates outward, because the field equations are local, and the causal cones constrain influence. Even singularities where classical description fails are hidden behind horizons in the standard picture. Cosmic censorship is not proven, yet it is consistent with every observed strong field event, from X-ray binaries to the gravitational wave catalogue of mergers. Historically, that caution was earned the hard way. Early solutions of Einstein's equations contained strange regions and coordinate artifacts, and it took decades to learn which features were physical and which were mirages of math. That is the first ranking, and it matters because it sets the burden of proof. Collapse to a larger black hole is the most plausible outcome under known physics, and it is the baseline we must beat. Transition. If the verdict seems anticlimactic, remember what it costs. It means the universe hides the paradox by making it ordinary. Now we allow conditional possibilities, because the story is also a stress test for quantum gravity. In speculative models, a white hole phase might exist briefly, either as a bounce or as a metastable boundary condition, appearing only when curvature approaches the Planck scale. These scenarios do not rewrite the exterior instantly, and that constraint is crucial for realism. They change how the horizon behaves under perturbations, and that changes how waves and fields are absorbed or reflected, especially in the narrow region just outside the photon sphere. A brief white hole phase could produce bursts, not as magic, but as delayed release of previously trapped energy. If in falling matter is temporarily stored and then re-emitted, the timing could look like an aftershock, sharp, bright, and slightly late compared to the merger peak. It could also produce gravitational wave echoes or anomalous ring-down modes if an effective cavity forms near the photon sphere. Visually imagine ripples on a dark pond hitting a circular wall, returning in faint repetitions, each pass losing energy as it leaks outward. The details would be technical but not arbitrary, because the echo spacing would be set by light travel times in the near-horizon geometry. In simple models, the delay scales with the mass, and with how close the reflective surface sits to the classical horizon, turning microphysics into a measurable clock. But the standard for evidence must be harsh, because we have learned how easily patterns appear in noise. A single odd event is not a discovery, because noise, modelling error, and astrophysical clutter can mimic small deviations, especially when templates are imperfect. Gravitational wave data analysis is a discipline of humility, built on matched filtering and careful calibration. Small phase errors, unmodelled higher harmonics, or glitches can leave residuals that look like extra structure, and the human brain is eager to interpret them as signals. Strong evidence would look like a statistically robust population of anomalies, not one dramatic outlier. Echo spacing would scale with mass, ring-down mode relationships would violate Kerr expectations, and the pattern would persist across detectors and pipelines, surviving changes in priors and waveform families. A second line of evidence would be correlated multi-messenger counterparts to otherwise black hole-like mergers. A prompt electromagnetic flash, or a neutrino cluster, tightly timed to the merger would be hard to dismiss, because vacuum black hole mergers are expected to be quiet. The timing would matter as much as the brightness, because coincidence is the enemy of inference. A flash arriving within seconds, with localization consistent across instruments, would force us to ask what material or mechanism was present near the horizon at the decisive moment. A third line would be direct behavior that looks like one-way emission, sustained and repeatable. An object that persistently emits while refusing accretion signatures would challenge the horizon boundary condition itself, because ordinary compact objects heat up when fed. Even then, we would still ask whether the culprit is a white hole in the strict time-reverse sense. Exotic compact objects, reflective surfaces, and quantum-modified horizons can imitate parts of the signature without being true time reversals, and nature may choose the imitation over the ideal, so we rank the speculative branch as plausible only with new physics and only with disciplined inference. It is not ruled out, but it is not licensed by classical stability or thermodynamics, which both lean relentlessly toward absorption and settling. Transition. The biggest claim sits beyond signals and templates. Could the collision create a new universe, and what would that even mean? In modern cosmology, a new universe usually means a causally disconnected region, not a bubble floating beside us in ordinary space. It can be a baby universe that buds off behind a horizon, or an inflating patch that becomes its own space-time domain with its own future infinity. The language sounds poetic, yet the mathematics is sober, because general relativity already allows non-trivial topology in principle. A pinch-off is a geometric statement. A throat can narrow until causal curves from one side cannot reach the other, leaving two separate causal futures. Some ideas frame this as cosmological natural selection, an attempt to give the multiverse a kind of evolutionary logic. Black holes might seed new regions with slightly varied constants, and universes that make more black holes become more common, not by intention but by branching. A white hole collision sometimes gets folded into that narrative as a trigger, because it highlights time reversal and boundary conditions. If a throat forms and pinches off, the interior could evolve as a separate expanding region, and from inside it might even resemble a Big Bang-like beginning. The crucial point is causal disconnection, and it is easy to misunderstand. If the new region is behind horizons, it cannot send signals back to our side once the geometry seals, no matter how dramatic the interior expansion becomes. From our perspective, even a real baby universe would be inferred indirectly, through bookkeeping at the boundary. It would look like missing energy, altered ring-down accounting, or an unexplained channel that carries information away, though even that inference would be model-dependent. That indirectness is not a failure of instruments, it is the definition of horizons. Event horizons are global causal boundaries, and they enforce what can be observed at infinity, turning some questions into statements about what cannot be asked operationally. So the phrase "create a new universe" can be true in a technical sense, while remaining observationally silent. The most dramatic interior story can be quarantined from the exterior forever, leaving us with only a mass, a spin, and the fading tones of ringdown. This also answers the fear of a space-time tear, the cinematic idea that a merger rips reality open across the sky. General relativity does not predict a universe-wide rupture from a localized merger, even with extreme curvature, because curvature does not automatically spread as a crack. Instead, it predicts quarantine, and the visuals should reflect that restraint. The violent dynamics are wrapped in horizons, and the exterior relaxes toward a new Kerr geometry, with shifted mass and spin, while gravitational waves carry away the last asymmetries like smoke thinning in air. If quantum gravity changes that, it must still respect causality in the exterior, or it must show us exactly where causality fails. Either way, the burden is on a concrete model that can be tested, not on a metaphor that cannot be falsified. So what would change our minds, in practice? Not in fantasy or in a single sensational plot twist. We would need repeated high significance deviations in ringdown spectra, including extra long-lived modes inconsistent with Kerr and consistent across different analysis groups. We would need echo claims that survive skeptical statistics, including look elsewhere penalties and cross-run calibration changes. We would need coherence across many events, not one lucky residual, and the effect would need to scale correctly with mass and redshift. We would need correlated electromagnetic or neutrino counterparts that match merger times, while ruling out neutron stars and disk-driven flares. The counterpart would need a consistent energy budget and repeatable phenomenology, so that rare coincidence stops being a refuge. We would need a direct observation of an object behaving like a one-way emitter, not just a transient. Persistent emission without accretion signatures would force a rewrite of boundary conditions, because it would imply outward flow without the usual inward supply. Future detectors make this more than philosophy, because they change what can be resolved in the waveform. Third-generation ground observatories can resolve more ringdown modes, and LISA can accumulate years of phase information in supermassive inspirals, tightening the noose around subtle deviations. Multi-messenger networks can also close loopholes, especially when timing is precise and coverage is wide. Wider gamma-ray coverage, better neutrino sensitivity, and faster follow-up reduce the chance that a real counterpart slips away, and they reduce the temptation to over-interpret ambiguous hints. Still, the final verdict must be honest, because mystery is not the same as probability. The most likely outcome is a black hole merger, because white holes are unstable and entropy favours absorption, and because typical perturbations drive the system toward a trapped horizon. A catastrophic space-time tear is unlikely, because general relativity localizes failure behind horizons. An explosive transient or baby universe channel remains speculative, but testable in principle, and that is the line between science fiction and patient measurement. We end where we began, with the swallow and the fountain as a mirror held up to time itself. The collision is less a prediction than a probe of why time has a direction, and why the universe seems to remember the past but not the future. If a white hole ever exists, it would be an argument about entropy made physical, not just philosophical. It would force us to ask whether information truly escapes, or only changes which horizon owns it, and whether escape is even a meaningful word from far away. The universe is already running the experiment in darkness, at distances where our eyes see nothing but our instruments hear everything. Our task is to keep listening to its most extreme events, until theory and data finally disagree in public, and the disagreement points to something real. Closing beat. Opposites may meet only in the equations, until detectors become sensitive enough to catch reality doing something stranger than theory. We began with a simple, impossible picture, then learned that collision near a horizon is never a crash of objects, but a rewrite of geometry. Black holes are the universe's best-tested one-way worlds, mapped by mass and spin, heard in chirps and ringdowns, and sketched by light bent into crescents. White holes, by contrast, live mostly in diagrams and time reversals, demanding exquisitely tuned beginnings, and resisting survival in a universe full of photons, neutrinos, dust, and tidal noise, across our chapters the same threads kept tightening until they felt less like speculation and more like a set of filters the cosmos must pass. Classical general relativity favours trapped surfaces that form locally and persist, while thermodynamics favours area growth, not area unwinding, and the generalised second law turns a lasting white hole into an entropy miracle. Even defining a meeting forced humility, because event horizons are global and future-defined, while simulations chase apparent horizons that can shift with slicing and with the choice of boundary conditions. When we finally brought the opposites together, the most consistent story was also the least cinematic, yet somehow the most profound. In an ordinary environment, a white hole is likely poisoned by tiny perturbations that blue shift near the horizon, collapsing the past horizon into a future one, and turning the encounter into a black hole merger in disguise. If anything exotic survives, it would probably be brief and subtle, a transient phase that leaves fingerprints rather than fireworks, extra ring-down structure, altered damping, energy bookkeeping tension, or faint late-time echoes that must be separated from noise with ruthless statistics. And still, we kept one door open, because the hardest questions here are not about spectacle, but about rules. Quantum gravity might allow a short-lived white hole-like boundary, a bounce delayed by extreme redshift, or even a pinch-off that hides a baby universe behind a horizon, leaving our side almost perfectly silent. If that happens, the only clues may be operational and indirect, a mismatch in mass and spin inferred from inspiral versus ring-down, a population-level scaling law for echo delays, or a rare multi-messenger flash that refuses to fit ordinary accretion physics. So the journey ends where it began, with horizons not as surfaces, but as decisions about which futures are allowed. The deeper we looked, the clearer it became that the central mystery is not whether space-time tears, but whether the universe ever permits a stable reversal of its causal bookkeeping even for an instant. In that sense, the black hole and the white hole are not just opposites, they are competing boundary conditions, and the cosmos seems biased, overwhelmingly toward the one that swallows. What remains unresolved is precisely what makes this thought experiment worth the trip. Which collision history is actually permitted? Horizon merger, close encounter with mass transfer, or a nearby ejection event? And what would count as a true meeting when the horizon itself depends on the entire future? What boundary condition would a white hole horizon obey in a dynamical, non-empty universe? Perfect emission, partial reflection, or rapid collapse into absorption? And how would energy flow respond when the first stray photons arrive? And if a quantum gravity loophole exists, can it produce signatures that are falsifiable, repeatable, and distinct from mundane systematics, rather than forever retreating into ambiguity? These are not loose ends, they are the map of where physics still lacks a final language. Because every time we asked about a white hole, we were really asking about the arrow of time, about whether entropy is a law or a boundary condition, and about whether horizons are absolute or emergent. A black hole, white hole collision, is a paradox staged in the most extreme theatre, but the true drama is whether causality can be locally negotiated or only globally enforced. If the answer is only globally, then the universe protects itself by turning would-be fountains into sinks long before they can contradict the future. And yet, even the conservative verdict carries a kind of wonder. If the most likely outcome is an ordinary Kerr remnant, then the lesson is that the universe has an attractor, a way of smoothing wild initial conditions into a stable, one-way geometry. If the unlikely outcome is real, then the lesson is even stranger, that the horizon can briefly behave like a mirror, or a valve, or a seam, and that the rules of quantum gravity can leak into signals we might actually measure. Either way, the impossible encounter becomes a practical test, because it tells us exactly what to listen for, and exactly how hard it will be to prove. In the end, the collision does not promise to destroy space-time, at least not in any way that spills into our cosmos. The more consistent picture is that space-time rebalances by forming a larger trapped region, keeping curvature hidden, keeping censorship intact, and paying the thermodynamic bill with increased area. If a baby universe is seeded, it is likely sealed behind that bill of exchange, a causal divorce whose paperwork is almost impossible to read from our side. But the opening question still matters, because it was never only about two exotic objects. It was about whether the universe can host two incompatible one-way doors in the same place, and whether their overlap forces a new rule to appear. The best answer we have is that, Under known physics, the doors do not annihilate, they align, and the arrow of time wins by default, unless quantum gravity can prove otherwise in a way the sky cannot hide, and that is the final twist. The most mysterious thing about black holes is not that they are dark, but that they are precise, turning gravity into a spectrum of predictions we can test. If white holes exist only as fleeting phases or mathematical shadows, then they are still useful, because they mark the boundary between what our equations allow and what the universe actually chooses. The collision, real or imagined, becomes a mirror held up to causality itself, and it asks whether the future is merely described by physics or partly defined by it. So, somewhere in the dark between galaxies, the forbidden fountain may never truly meet the ultimate sink, at least not as stable opposites. Yet by chasing that encounter, we discovered where our confidence is strongest, where our ignorance is sharpest, and where observation can still surprise theory. The darkest places in space may not be where reality ends, but where the next revision begins, quiet at first, then undeniable. If you want to follow the edge of that revision, watch the catalogues grow, watch the ringdowns sharpen, and watch the searches for echoes mature from headlines into statistics. Because if space-time ever does blink, it will not announce itself with certainty. It will whisper in patterns across many events, until the whisper becomes a law. And when that happens, the impossible encounter will have done what it was always meant to do. Force us to learn what the universe refuses to violate, and what it might, at last, allow. Back at the beginning, we asked whether a black hole and a white hole could collide and whether spacetime would tear, flare, or birth a new universe. After the journey through horizons, entropy, instability, and detection, the most consistent answer is that spacetime does not break. It chooses a common future, and the encounter collapses into a larger black hole, unless a brief quantum gravity loophole leaves only faint testable fingerprints. A black hole-white hole collision is less a cosmic explosion than a referendum on the universe's deepest commitments: causality, entropy, and the meaning of a boundary. Even if the white hole never survives long enough to be seen, the question remains a compass, pointing us toward the next place physics must change. So keep listening to the universe in gravitational waves, and treat every clean ringdown and every stubborn anomaly as a clue, not a conclusion.